human beings have reflected on life and the universe for millennia. As a species, we have been aware of space since we could look at the night sky. One of the first notable ideas about the universe goes back to ancient Greece, around 600 BC, and to Hindu writings such as the Bhagavad Purana and the Bhagavad Gita. In the modern era, Newton and Einstein also made significant contributions. Today's narrative will include some interesting mysteries of the cosmos. We will start with our own solar system, the alien worlds, and then we will advance in cosmology, such as the formation of the moon, the Earth's magnetic field, and what it does for us, how it creates the aurora borealis, and going back to the beginning of the universe, the Big Bang. So, what is the evidence for the Big Bang theory? What was it like? When did it occur? But most importantly, how do we know, and why are they difficult questions to answer? The moon is one of the largest objects in our solar system, almost as large as Mercury and significantly large compared to Earth. This similarity in size raises an interesting question. How did the Earth and moon form this way? Why do these two bodies orbit one another? There are also some intriguing facts about the Earth and moon. For example, this beautiful image, taken by a space probe that orbited Mars a few years ago, shows the Earth and moon from Mars' perspective. A fascinating fact about the moon is that it has very little iron in its core, unlike the Earth, which has a lot of iron in its core, responsible for its magnetic field. This difference is disconcerting because if the moon formed in the same region as the Earth, why does the Earth have so much iron in its core while the moon has so little? Another interesting aspect is the amount of spin within the Earth-Moon system. The moon is quite large compared to the Earth. It orbits it quickly, and both the Earth and moon rotate on their axes. A fundamental principle of physics is that spin, or angular momentum, does not appear out of nowhere. It must come from somewhere, so when you see the Earth and moon spinning rapidly and the moon orbiting the Earth rapidly, there must be an explanation for that. Why is there so much angular momentum and spin in the Earth-Moon system? One of the greatest achievements in human history was when we landed on it in 1969. During this mission, we collected lunar rocks and brought them back to Earth. Scientists discovered that the composition of these lunar rocks is very similar to that of terrestrial rocks, suggesting that the moon and Earth may share the same origin. By examining the decay of radioactive elements within the lunar rocks, we could determine their age. These rocks appear to be between 30 and 50 million years younger than Earth, although this difference may not seem significant. Since the Earth is about 45 billion years old, it indicates that the moon formed slightly later than the Earth. Another interesting fact has to do with isotopes, which are different forms of a single element. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The same concept applies to oxygen, too. The proportion of these different forms of oxygen can be measured very accurately in various parts of the solar system. These proportions differ depending on a planet's proximity or distance from the Sun at the time of its formation. However, on Earth and the Moon, these proportions are very similar, indicating a common origin. So here we have a small question. The Moon is slightly younger than the Earth. It spins rapidly. It is composed of similar materials, but it has very little iron. What is the explanation for this? There is a widely accepted theory that explains all these things. Some people question it, which shows how science works. It is not 100% correct or accepted, but it makes sense according to the evidence. Scientists have several theories about how the Earth and Moon formed. One of the most accepted theories is the giant impact hypothesis. The theory suggests that about 50 million years after the Earth formed, another planet the size of Mars was very close to Earth. This planet collided with the Earth in a glancing blow, tearing off a large amount of debris without hitting the Earth's core. When planets form, heavy elements like iron sink to the center. So when this collision occurred, the torn material had little iron, since most of the iron was already in the Earth's core. This collision also caused a great rotation, similar to kicking a soccer ball to make it spin and curve. This explains why the Earth-Moon system has so much spin. The Moon formed from the remains of this collision, so it has materials and isotopes similar to those of Earth. Since the collision occurred 50 million years after the formation of the Earth, this explains why the Moon's rocks are slightly younger than those of the Earth. It seems that the Moon formed from a planetary collision about 45 billion years ago, and all the evidence supports this idea due to these 4 observations about the Earth and Moon, in addition to the fact that we went to the Moon, collected samples, and analyzed them in the laboratory, which further supports the theory. Another interesting point is that this collision not only formed the Moon, but also played an important role in shaping the Earth's future. The impact likely tilted the Earth's axis, so we experience seasons. Without this inclination, our planet might not have the same climatic patterns that support diverse life forms. The presence of the Moon also helps stabilize the Earth's rotation, preventing extreme changes in its inclination over long periods, which would have drastic effects on our environment. In addition, the gravitational interaction between the Earth and the Moon creates the tides, which have influenced the evolution of life on Earth. The regular rise and fall of oceanic levels has affected coastal ecosystems and human activities for millennia. In addition, the Moon is slowly moving away from the Earth. Measurements show that the Moon moves about 38 centimeters away from the Earth each year. This slow separation affects Earth's rotation and the length of our days. Millions of years ago, days were shorter, and as the Moon continues to move away, days on Earth will lengthen gradually. While the giant impact hypothesis is most accepted, other fascinating theories exist. One of them is the fission theory, which suggests that the Moon was part of the Earth, but separated due to the rapid rotation of the planet in its beginnings. This rapid spin caused a piece of material to break off from Earth and form the Moon. However, this theory fails to explain the Moon's current orbit or the mechanics of such a separation. Another theory of interest is the capture theory. According to this idea, the Moon formed elsewhere in the solar system and was later captured by the gravitational force of the Earth. This could explain why the Moon's composition differs from that of the Earth. However, capturing such a large body without it breaking apart seems unlikely. Despite these theories, the exact process of the Moon's formation remains a subject of scientific research and debate. The unique relationship between the Earth and the Moon also has a significant impact on life here. The gravitational force of the Moon creates the tides, which have influenced the evolution of life and the development of human civilizations. The regular rise and fall of oceanic levels has affected coastal ecosystems and human activities for thousands of years. The Earth-Moon system is a fascinating subject that provides information about the formation and evolution of planetary bodies. The differences in composition, the shared angular momentum, and the continuous dance between Earth and its only natural satellite tell a complex and intriguing story about our place in the cosmos. This photo was taken by telescope in 1917. It shows a blurry spot with some dark markings. Even respected astronomers of the time thought these marks could be signs of vegetation. That idea was disproven when spacecraft began to visit Mars. The first was Mariner 4 in 1965, which sent grainy images of the surface. President Lyndon Johnson then reflected that life, as we know it, might be more unique than previously thought. Today, many spacecraft have visited Mars, and we now see a world with geological giants, like a canyon that stretches halfway across the planet, called Valles Marineris. The Earth's Grand Canyon would fit inside one of its side channels. Mars also has enormous volcanoes and evidence of past lakes and possibly oceans. Currently, the Curiosity rover is exploring the bed of an ancient dry lake and has found indications of organic molecules and minerals that form in still water. We now know that Mars was similar to Earth about 3,000 to 3,200 million years ago, with rivers, seas, and oceans. It could have been an inhabited world, but we don't know if life began there. This changes our vision of Mars. A planet with water has everything necessary to build a civilization and sustain life. Even if there were no Martians billions of years ago, and even if there are no Martian microbes today, there could be Martians in the future because the Martians will be us. Mars, often called the Red Planet, has always captivated our imagination with its intriguing landscapes and the possibility of life beyond Earth. Among the many mysteries that Mars presents, one of the most interesting is what happened to its water. Evidence suggests that billions of years ago, Mars had large amounts of liquid water flowing through rivers and possibly even large oceans. Today, however, Mars is a desert with only traces of water in its atmosphere and at the polar caps. So, what caused this dramatic transformation? To understand the disappearance of water on Mars, we have to look back to the planet's early history. Geological features such as river valleys, lake beds, and mineral deposits indicate that Mars once had a much denser atmosphere that would have allowed liquid water to exist on its surface. This denser atmosphere likely created a stable climate that maintained the pressure and temperature needed for liquid water. However, over billions of years, Mars lost most of its atmosphere, leading to the arid conditions we see today. One of the main theories to explain the loss of Mars' atmosphere is the influence of the solar wind. The solar wind is a stream of charged particles emitted from the sun. Unlike Earth, Mars lacks a global magnetic field to protect its atmosphere from these particles. Earth's magnetic field acts as a shield, deflecting the solar wind and preventing it from stripping away our atmosphere. Mars, however, lacks that protective barrier, so the solar wind interacts directly with the Martian atmosphere, gradually eroding it over time. This process, known as atmospheric sputtering, involves solar wind particles colliding with atmospheric molecules and launching them into space. As the Martian atmosphere thinned, the planet's ability to retain heat decreased, and the drop in atmospheric pressure and temperature caused the remaining liquid water to freeze or sublimate. Sublimation is the process by which a solid becomes a gas directly, without passing through the liquid state. This process likely contributed to the loss of surface water from Mars, as the low pressure and temperature made it unsustainable for liquid water to remain. The weak gravity of Mars also played an important role in the loss of its atmosphere and water. Mars has only about 38% of Earth's gravity, meaning it cannot retain atmospheric gases as effectively as Earth. Over time, lighter molecules, such as hydrogen and oxygen, which are essential components of water, escaped into space. This gradual leakage of gases further depleted the Martian atmosphere, exacerbating the loss of water. Volcanic activity on Mars was once far more intense than today. At the beginning of its history, Mars suffered significant volcanic eruptions, releasing large amounts of gases into the atmosphere. These volcanic activities could have replenished the atmosphere and maintained a greenhouse effect that kept the planet warm enough for liquid water. However, as volcanic activity decreased, so did the replenishment of the atmosphere. Without the addition of new gases, the atmosphere continued to thin, contributing to the cooling and desiccation of the planet. Despite the loss of much of its atmosphere and surface water, Mars still possesses significant amounts of water in the form of ice. Recent discoveries by the rovers and orbiters have revealed vast deposits of water ice just below the surface, especially in the polar regions. Radar data from missions, such as the Mars Reconnaissance Orbiter, have detected large underground ice layers that could potentially contain more water than all the Great Lakes of the Earth together. In addition, some scientists speculate that liquid water may exist in underground lakes isolated by ice and Earth. These hidden reserves offer a glimpse into Mars' wetter past and hope for exploration. The state of the iron core of Mars plays an important role in the history of the planet and its current conditions. Unlike Earth, which has a molten iron core that generates a strong magnetic field, the iron core of Mars is largely solidified, resulting in a weak and irregular magnetic field. This lack of a protective magnetic field left Mars vulnerable to the solar wind, a stream of charged particles emitted by the sun, for billions of years. These particles tore away much of the atmosphere of Mars, leading to the loss of water on the surface. The weakened magnetic field influenced not only atmospheric erosion, but also the planet's ability to maintain a climate capable of sustaining liquid water. Understanding the fate of water on Mars is crucial not only for planetary science, but for future human exploration. Water is essential for life and a vital resource for astronauts on Mars, It can be used for drinking, growing food, and producing oxygen and hydrogen as fuel. By unlocking the secrets of Mars' lost water, we can better prepare for human missions to the planet. The utilization of in situ resources, the practice of using local materials for human needs, will be key to maintaining long-term missions on Mars. If we can locate and extract water from the Martian subsoil, the feasibility of a permanent human presence on Mars will improve. Mars serves as a natural laboratory for studying the evolution of planetary atmospheres and the factors influencing their stability. By comparing Mars to Earth and other planets, scientists can develop better models for predicting the future climate of our own planet and the potential for life on other worlds. In recent years, missions such as NASA's Perseverance rover and the European Space Agency's ExoMars mission have focused on searching for signs of past life on Mars. These missions aim to study the geology of the planet and look for biosignatures, chemical or physical markers that indicate the presence of past or present life. The presence of water is a critical factor in these investigations, as it is a key ingredient for life as we know it. By understanding where water existed on Mars and how it interacted with the planet's geology, scientists can better assess the potential for ancient life there. The history of water on Mars is a complex story of planetary changes and the dynamic processes shaping our solar system. Although many questions remain, each new discovery brings us closer to understanding this enigmatic planet. The history of water, atmosphere, and climate on Mars continues to captivate scientists and enthusiasts, driving the exploration and study of our neighboring world. This is a current image of Mars taken by a spacecraft. Wherever we look, we see evidence of rivers, so Mars may have been a world that harbored life about 3 billion years ago. We now know that there is water, minerals, and practically everything needed to sustain human life and a civilization on Mars. So Mars is not only a war-bearer or a terrifying red object, but a bearer of opportunities and music. We hope that one of the most iconic and lasting features of our solar system is the Great Red Spot of Jupiter. This enormous storm, larger than Earth, has been raging on Jupiter for at least 400 years, and possibly longer. The Great Red Spot is a gigantic swirling storm that has fascinated astronomers and scientists since it was first observed. But what exactly is the Great Red Spot, and why has it lasted so long? Let's delve into the details to uncover the secrets of this colossal storm. The Great Red Spot is a high-pressure region in Jupiter's atmosphere that produces an anticyclonic storm rotating counterclockwise in the planet's southern hemisphere. Music. This storm is so large that it can easily be seen from Earth through telescopes. In fact, it is about 13 times the diameter of our planet. The edges of the storm rotate faster than its center does. The storm's distinctive reddish color is one of its most intriguing features. Scientists are still unsure what causes this striking hue. Some theories suggest that the red color comes from chemical substances present in Jupiter's atmosphere, such as phosphorus, sulfur, or organic compounds that may be altered by ultraviolet light from the sun. Another theory is that the color could come from the depths of the storm, with different chemicals being stirred up from below. Regardless of its origin, the red color makes the Great Red Spot stand out against Jupiter's turbulent atmosphere of white, brown, and yellow bands. One of the biggest mysteries of the Great Red Spot is its longevity. On Earth, storms usually last days or weeks at most. Music, however, the Great Red Spot has persisted for centuries. This incredible durability is partly due to Jupiter's unique atmospheric conditions. Jupiter is a gas giant, meaning it lacks a solid surface like Earth, but is composed primarily of hydrogen and helium with traces of other gases. This allows storms to last longer because there is no land to interrupt them. In addition, its size and rapid rotation contribute to the Great Red Spot's stability and longevity. Jupiter's rapid rotation plays a key role in maintaining the Great Red Spot. The planet completes a rotation in a little less than 10 hours, much faster than the 24-hour day of the Earth. This rapid spin creates strong jet streams that help contain the Great Red Spot. These jet streams act as barriers that keep the storm confined to its region and prevent it from dissipating. The interaction between these jet streams and the storm helps maintain its structure and intensity. Despite its longevity, the Great Red Spot isn't eternal. Observations made during recent decades show that the storm is gradually shrinking. When first measured in the late 19th century, the Great Red Spot was about 25,000 kilometers wide. Today, it is less than half that size. Scientists are closely monitoring this reduction to understand why it is happening and what it could mean for the future of the storm. The reasons for this gradual contraction are not fully understood, but could be due to changes in the dynamics of the atmosphere of Jupiter or to interactions with other storms and atmospheric characteristics. The dynamics within the Great Red Spot are complex and still not fully understood. Winds can reach speeds of up to 400 miles per hour. These powerful winds create towering clouds that rise above the surrounding atmosphere. The storm also has a layered structure with different temperatures and wind speeds at different altitudes. The study of these layers helps scientists to learn more about the behavior of the storm and its impact on the atmosphere of Jupiter. The top of the Great Red Spot is colder than the surrounding clouds, indicating that the storm extends deep into Jupiter's atmosphere. In recent years, NASA's Juno spacecraft has provided unprecedented data about the Great Red Spot. Juno, which has been orbiting Jupiter since 2016, carries a suite of instruments designed to study the atmosphere, the magnetic field, and the internal structure of the planet, music. Juno's close flybys of the Great Red Spot have revealed new details about the storm's depth and composition. For example, Juno has shown that the storm extends deeper into Jupiter's atmosphere than previously thought, possibly hundreds of miles. This depth suggests the Great Red Spot is a towering structure with deep roots in the planet's envelope. The Great Red Spot also offers a window to understanding other planetary atmospheres, including those of exoplanets outside our system. By studying this storm, scientists could develop models to predict weather patterns on other gas giants and potentially habitable worlds. This knowledge expands our understanding of how atmospheres work throughout the universe. The insights gained from the Great Red Spot help scientists identify similar characteristics in exoplanets and understand the dynamics of distant worlds. The mystery of the Great Red Spot continues to captivate us and reminds us of the immense forces at work in our solar system. Each new discovery about the Great Red Spot brings us closer to unraveling its secrets, but also highlights how much we still have to learn about Jupiter and other giant planets. The persistence and changing nature of the storm make it a laboratory for studying the behavior of atmospheres under extreme conditions. In addition to its scientific importance, the Great Red Spot has also become a cultural icon that has appeared in countless works of science fiction, art, and literature, symbolizing the mysteries and wonders of our solar system. The vivid appearance and lasting presence of the storm make it a favorite subject for professional astronomers and amateur stargazers alike. Observing the Great Red Spot through a telescope is an exciting experience that connects us to the vast universe beyond our planet. Understanding the Great Red Spot also helps us appreciate the delicate balance of Earth's atmosphere. Although the storms on our planet are smaller, the underlying principles of atmospheric dynamics are similar. The future of the Great Red Spot remains uncertain. Will it continue to shrink and eventually disappear, or will it stabilize and persist for many centuries more? Scientists are eager to find out, and ongoing observations from missions like Juno will be crucial to answering these questions. The data collected by Juno and future missions will help scientists build more accurate models of Jupiter's atmosphere and understand the behavior of its storm. Jupiter, the largest planet in our solar system, is known for its many fascinating features, from its iconic Great Red Spot to its vibrant cloud bands. But one of its most dramatic features is a series of scars on its surface caused by impacts from comets and asteroids. These impact scars offer a window into the violent history of our solar system and the forces at work on Jupiter. One of the most famous events that left scars on Jupiter occurred in July 1994, when comet Shoemaker-Levy 9 collided with it. This was the first time humans had the opportunity to witness such a cosmic event in real time. Shoemaker-Levy 9 was discovered by astronomers Carolyn and Eugene Shoemaker and David Levy in March 1993. The comet had fragmented into several pieces, probably due to a previous close encounter with Jupiter's gravity. As the fragments of Shoemaker-Levy 9 approached Jupiter, astronomers prepared to observe the collisions. When the impacts began on July 16, 1994, they produced spectacular results. Each fragment crashed into Jupiter's atmosphere at a speed of about 60 kilometers per second, releasing immense amounts of energy. The impacts created huge fireballs, some rising up to 3,000 kilometers above the clouds. These collisions left dark marks on Jupiter's surface, visible even through small telescopes on Earth. The largest impact, caused by fragment G, left a mark more than 12,000 kilometers wide, larger than Earth's diameter. Composed of dark debris, the marks gradually faded over the following months, but their initial visibility highlighted the enormous magnitude of these impacts. The event provided invaluable data to scientists, offering information about the behavior of comets and planetary atmospheres. The scars of Shoemaker-Levy 9 were not permanent, but they highlighted the vulnerability of even the largest planets to collisions. Jupiter's immense gravity makes it a prime target for comets and asteroids, acting as a kind of solar system vacuum cleaner by capturing or redirecting these objects. Jupiter helps protect the inner planets, including Earth, from potential impacts. However, this protective function also means that the atmosphere of Jupiter frequently suffers the impact of these. In recent years, amateur astronomers have continued to detect new impacts on Jupiter. On July 19, 2009, Australian amateur astronomer Anthony Wesley observed another significant impact. He noticed a new dark spot near the south pole of Jupiter, similar in appearance to the scars left by Shoemaker-Levy 9. Subsequent observations confirmed that this spot was caused by the impact of a comet or asteroid. This event demonstrated again Jupiter's role as guardian of the inner solar system, receiving the impact of a potentially dangerous object. The scars on the face of Jupiter are not only a testament to its turbulent environment, but also a reminder of the dynamic nature of our solar system. These impact events help scientists understand the frequency and scale of collisions in space, shedding light on the processes that have shaped planets over billions of years. The study of these impacts on Jupiter can also provide clues about the early history of the solar system, an era in which these types of collisions were much more common. Jupiter's ability to capture and absorb impacts also has implications for the study of exoplanets, or planets outside our solar system. By understanding how Jupiter interacts with comets and asteroids, scientists can develop models to predict the behavior of gas giants in other systems. This knowledge is crucial for assessing the potential habitability of exoplanets, as gas giants like Jupiter can play a similar protective role in those systems, in addition to functioning as cosmic shields. The scars of Jupiter offer information about the composition and structure of Jupiter's atmosphere. When an impact occurs, an explosion of energy is released that can penetrate deep into the planet's atmosphere. By observing the aftermath of these impacts, scientists can study the resulting disturbances and gather information about atmospheric layers. This helps them understand the complex climatic patterns and chemical processes that occur on Jupiter. The scars left by the impacts also reveal the enormous power of these collisions. The energy released by the Shoemaker-Levy 9 impact, for example, was equivalent to millions of nuclear bombs exploding simultaneously. Such events underscore the importance of monitoring near-Earth objects and developing strategies to mitigate potential threats from space. The scars of Jupiter are a reminder of the forces that shape our solar system. They highlight the continuous dance of celestial bodies and the constant change that characterizes the cosmos. While the scars may eventually fade, the knowledge gained from studying them endures, contributing to our understanding of planetary science and the dynamics of our solar system. Mars continues to surprise scientists with its mysterious phenomena, and one of the most intriguing discoveries is the presence of strange dark stripes on its surface that seem to flow. These stripes, known as recurring slope lines, are found on steep slopes, such as the walls of craters and the sides of canyons. They appear to darken and lengthen during the warm seasons and fade when it is colder. Scientists believe that these stripes could be caused by salt water that temporarily flows down the slopes when temperatures rise. Although the exact origin and nature of the water is unknown, the idea that there is water on Mars is not new. Mars shows many indications that a long time ago, it had a lot of liquid water. Mars had rivers, lakes, and perhaps even oceans. We can see ancient riverbeds and lake basins on its surface. However, today Mars is mostly dry, with only a little ice at its poles and some water vapor in its thin atmosphere. These dark stripes were first observed by the Mars Reconnaissance Orbiter, a spacecraft that has been studying Mars from orbit since 2006. The MRO has a special camera called the High-Resolution Imaging Science Experiment, which can take very detailed images of the Martian surface. This pattern suggests that the stripes could be related to liquid water that might flow when it is warmer and freeze or dry out when it is colder. To better understand the RSL, scientists observed the conditions on Mars where these stripes appear and discovered that they normally form on sun-facing slopes, where it is warm enough for ice to melt. However, Mars is still very cold compared to Earth, and pure water would freeze quickly. This led scientists to think that the water in the RSL must be mixed with salt. The salt water can remain liquid at lower temperatures because the salts reduce the freezing point of the water, similar to how salt is used to melt road ice during winter. The exact source of the water in these stripes remains a mystery. Some scientists think that the water could come from melting underground ice that seeps. Others believe that the water could come from the atmosphere, with water vapor absorbed by the salts in the soil and then becoming liquid when it heats. Both ideas are possible, but more research is needed to find the true source. Understanding the RSL is important for several reasons. First, if there is liquid water on Mars today, it increases the chances that life may exist there, even if only in small microbial forms. Water is essential for life as we know it, so finding liquid water on Mars is a big step in the search for Martian life. Second, the presence of water is important for future human missions to Mars. Astronauts could use this water to drink, grow food, and make fuel. However, there are also challenges and risks. Salt water could be very different from the water we're used to on Earth and could be harmful to both humans and any terrestrial microbes we carry. It is important to study these streaks carefully to understand what kind of water they contain and how it could affect future missions. In conclusion, the discovery of these dark streaks that ooze on Mars is a fascinating advance in our understanding of the red planet. They suggest that liquid water may still exist on Mars, at least during the warm seasons. This opens new possibilities to find life and supports the idea that Mars was once a more humid planet. As we continue exploring Mars, each new discovery brings us closer to understanding its mysteries and prepares us for the day when humans can set foot on its surface. The streaks that ooze from Mars are just one of the many clues that will help us unravel the secrets of our neighboring planet. In March 2004, the NASA rover Opportunity had just finished its 283 million-mile journey from Earth to Mars. In the following days, Opportunity took many photos of the surface of Mars, but one image surprised and confused the mission team. It showed what looked like a fuzzy white rabbit. This object quickly became known as the Martian rabbit. The Martian rabbit caused much excitement and confusion among scientists, who wondered what it could be. Was it a piece of the rover, a strange rock, or something completely different? The object appeared in several images taken by the rover, showing it from different angles. It had a furry appearance similar to that of a rabbit, which made it even more mysterious and intriguing. As scientists examined the images, they began to develop theories about what the Martian bunny could be. One idea was that it could be a piece of the rover itself, possibly a piece of insulating material or debris that had come off during landing. This theory made sense because the object did not look like a natural rock or any other known Martian feature. It seemed to be something out of place. However, before scientists could study it further, the Martian bunny did something unexpected and disappeared in images taken by the rover. The mysterious object was no longer visible. This sudden disappearance added another layer to the mystery. How can an object simply disappear from the Martian surface? There are some possible explanations for the disappearance of the Martian rabbit. One idea is that it was a piece of light material, such as plastic or fabric, that was blown away by the wind. Mars has strong winds that can move dust and small objects across the surface. If the Martian rabbit was a piece of light debris, it could have been lifted and blown away by the wind, disappearing from the view of the rover's camera. Another possibility is that the object was buried by Martian dust. Mars is a dusty planet, and dust storms can cover objects very quickly. If a dust storm passed through the area where the Martian rabbit was located, it could have buried the object under a layer of dust, making it invisible to the rover's cameras. Although the true identity of the Martian rabbit may never be known, the mystery highlights the challenges and surprises that come with exploring another planet. Mars is a complex and dynamic world, and even small, unexplained phenomena, such as the appearance and disappearance of the Martian rabbit, can teach us a lot about the planet. Each discovery, no matter how small, increases our knowledge of Mars and prepares us for future missions. When Johnson, a scientist at the United States Geological Survey, became intrigued by the mysterious object, he was assigned the task of finding out more about it. He soon found the bunny in other images taken by the rover's navigation camera and used special software from the NASA Jet Propulsion Laboratory to measure its size, which was about the size of a tennis ball. Then, there was again, in a photo of the rover's lander, Johnson saw a small white object that resembled the bunny seen in the previous photos. The team thought that a gentle wind had blown the object to a new location, under one of the ramps intended to help the rover roll over the surface of Mars. Scientists never exactly confirmed what it was, but they believed it was probably a piece of soft material from the landing vehicle. The landing vehicles were made of many different materials, but the most likely candidate was the white felt that surrounded each of the 3 gas generators in the airbags. In conclusion, the Martian bunny is one of the many fascinating enigmas that Mars presents to us. It appeared suddenly in the images taken by the Opportunity rover, causing excitement and curiosity, and then disappeared mysteriously, whether it was a piece of the rover, a light object blown by the wind, or something buried by dust. The Martian rabbit reminds us of the unpredictable and surprising nature of space exploration. As we continue studying Mars, we can expect many more mysteries and discoveries that will deepen our understanding of this intriguing planet. Saturn, the 6th planet from the Sun, is a world of wonders and mysteries. Among its most fascinating features is the strange hexagonal storm that swirls around its north pole. This geometric storm has captured the curiosity of scientists and space enthusiasts alike, as it presents a phenomenon different from any other seen on Earth or on any other planet in our solar system. Let's delve into the details of this remarkable and enigmatic storm discovered by the NASA Voyager spacecraft during its flybys in the early 1980s. Saturn's hexagonal storm is a massive and persistent weather pattern, different from the circular storms we know on Earth. This storm has a distinctive 6-sided shape that resembles a hexagon. Each side of the hexagon measures approximately 14,500 kilometers long, making it more than twice the diameter of the Earth. The storm also contains a powerful jet stream with winds reaching 320 kilometers per hour. What makes this hexagonal storm so intriguing is not only its size and shape, but also its stability. The storm has persisted for decades, showing little change in its structure or position. While storms on Earth can last days or weeks, this hexagon has remained in place for at least 40 years and possibly much longer. Scientists have proposed several theories to explain the formation and persistence of Saturn's hexagonal storm. One prominent theory suggests that the hexagon is formed by a pattern of standing waves in the atmosphere of Saturn. On Earth, standing waves can occur in the oceans and in the atmosphere, creating stable patterns that do not move with the flow of air or water. Similarly, Saturn's hexagon could be a standing wave created by the interaction of Saturn's atmosphere with its rapid rotation and internal heat. Saturn's atmosphere is composed mainly of hydrogen and helium, with traces of other gases like methane, ammonia, and water vapor. The rapid rotation of the planet, completing a turn in just over 10 hours, creates strong jet streams and turbulent weather. These jet streams interact in complex ways, leading to the formation of stable structures like the hexagon. The standing wave theory suggests that the hexagon is the result of these interactions with the wave pattern that blocks the storm in its distinctive form. Another theory proposes that the hexagon is related to the unique properties of the atmosphere of Saturn and its layered structure. Saturn's atmosphere has different layers, each with its own temperature, pressure, and composition. These layers can interact in ways that create stable geometric patterns. Laboratory experiments have shown that similar hexagonal patterns can be formed in rotating fluids, which supports the idea that the hexagon is a natural result of the atmospheric dynamics of Saturn. One of the most intriguing aspects of the hexagonal storm is its color in the images taken by the Cassini spacecraft of NASA, which orbited Saturn from 2004 to 2017. The hexagon appears in shades of blue and gold. The color variations are probably due to seasonal changes in the atmosphere of Saturn during the winter of the Northern Hemisphere. The hexagon appears blue, possibly due to the lack of sunlight and the resulting condensation of certain gases. As spring and summer approach, the hexagon changes to a golden hue, probably due to increased sunlight and the production of photochemical mists. During the first 5 years of the Cassini mission to Saturn, the hexagon at the planet's North Pole was impossible to see in visible light because it was winter. Winter on Saturn lasts about 7 years and keeps the North Pole in darkness. But in December 2009, spring arrived, and the sun shone again on the North Pole, allowing Cassini to capture the first detailed images of the hexagon of Saturn, showing features never seen before. Physicists at the University of Oxford helped explain the hexagon by simulating the interaction between Saturn's atmosphere and the rotating jet stream. They discovered that, by changing the speed of the jet stream and the atmosphere, they could create different shapes, including a hexagon. It turns out that Saturn's hexagon is formed by an intense jet stream that mixes with the surrounding atmosphere, and in its center, there's a huge rotating storm that has been there for decades. In 2013 and 2017, Cassini took closer images of the hexagon. These images were combined to create 2 videos from 2013 and 2017. However, a new mystery arose. What caused the hexagon's color to change during those 4 years? The Cassini mission provided a dataset on Saturn's hexagon that revealed previously unknown details. For example, Cassini observed a huge hurricane-like storm in the hexagon center, with a clearly defined eye and high-speed winds. This storm is surrounded by clouds that reach heights of up to 100 kilometers above the surrounding clouds. Cassini data also showed that the hexagon extends deep into Saturn's atmosphere, indicating that it is not just a surface feature, but a complex multi-layered structure. Understanding Saturn's hexagonal storm is not only solving a planetary puzzle, but also has broader implications for our understanding of atmospheric dynamics. The study of this storm can provide information on the behavior of fluids and gases under extreme conditions, helping scientists develop better models of weather patterns on Earth and other planets. The hexagon also serves as a natural laboratory to study the effects of rotation, convection, and interactions in planetary atmospheres. The persistence and stability of Saturn's hexagonal storm also raise questions about the long-term evolution of planetary weather systems. How are these patterns formed, and what factors determine their longevity? By studying the hexagon, scientists can better understand the processes that drive weather patterns on gas giants and other planets, both in our solar system and beyond. In recent years, scientists have used computer simulations to model the hexagon and test different hypotheses about its formation. These simulations have shown that rotating fluids can produce stable hexagonal patterns under certain conditions. By adjusting the parameters of these models, researchers can explore how different factors, such as the rotation speed of Saturn, the atmospheric composition, and internal heat, contribute to the formation and maintenance of the hexagon. Saturn's hexagonal storm continues to be a topic of active research and fascination. Each new discovery adds to our understanding of this extraordinary feature and the dynamic processes that shape planetary atmospheres. As future missions to Saturn and other gas giants are planned, scientists hope to collect even more data to unravel the secrets of the hexagon and other mysterious phenomena. In conclusion, Saturn's hexagonal storm is a striking and enigmatic feature that challenges our understanding of planetary climate. Its geometric shape, immense size, and lasting stability make it a unique phenomenon in our solar system. By studying the hexagon, scientists can obtain valuable information about the dynamics of Saturn's atmosphere and the broader principles that govern the behavior of fluids and atmospheric patterns. As we continue to explore the wonders of our solar system, Saturn's hexagonal storm remains a compelling reminder of the complexity and the beauty of the universe. Perhaps the greatest space mystery of all time is whether we are alone in the universe or even in our solar system. We have recently found indications that the answer could be out there, perhaps even on one of the moons of Jupiter and Saturn. Water is essential for life as we know it. Astrobiologists who study the possibility of life beyond Earth claim other necessary ingredients, such as certain chemical compounds and a constant energy source. Until recently, Earth was the only known world with liquid water. We now know that at least two other places, Jupiter's moon Europa and Saturn's moon Enceladus, have global oceans. There are also indications that there is water elsewhere, but what about the other ingredients for life? The icy moons Europa and Enceladus could have them too. When the Cassini spacecraft discovered a plume of water vapor and icy particles shooting from Saturn's moon, Enceladus, scientists wanted to know more. Originally, the Cassini was supposed to fly 3 times near Enceladus, but it ended up making 23 passes, learning more about the chemistry of the moon and the plume. Every time, they found a salty ocean beneath Enceladus' icy surface and strong indications of hydrothermal sources. These sources, similar to those at the bottom of Earth's oceans, release chemical substances that support tiny shrimp and other creatures. If Enceladus has similar sources, it could have the chemistry and energy needed for life. Alien shrimp? Meanwhile, on the moon of Jupiter, Europa, the clues from the Galileo mission suggest that it also has a global ocean. Later, the NASA Hubble Space Telescope detected possible plumes of water vapor. To find out more, NASA is developing a new spacecraft called Europa Clipper, designed to study Europa and further investigate this mystery. These moons have conditions that could be similar to those of Earth's deep oceans, where life thrives around hydrothermal sources. These sources support ecosystems teeming with life, including shrimp, crabs, and various microorganisms. These creatures do not depend on sunlight for energy, but on the chemical energy released by the sources, demonstrating that life can exist in extreme environments. Europa and Enceladus have thick ice layers covering their oceans. Scientists believe that under these icy layers there could be warm, salty oceans that may be habitable. The ice acts as a protective layer that shields the oceans from space radiation, making these moons some of the most promising places to look for life beyond Earth. The discovery of plumes on Enceladus was a major breakthrough. These plumes shoot out from cracks in the moon's ice layer, known as tiger stripes, and extend hundreds of kilometers into space. Cassini flew through these plumes, analyzing their composition and discovering water vapor, ice particles, and organic molecules. The presence of these organic molecules suggests that Enceladus contains the basic components of life. Cassini's findings also indicated that the plumes contain salts and other minerals that point to the presence of hydrothermal activity at the ocean floor. On Earth, hydrothermal sources harbor diverse ecosystems fueled by the chemicals released from them. If similar conditions exist on Enceladus, it opens the possibility that life may thrive in its hidden ocean. The NASA Europa Clipper mission, scheduled to explore Europa in more detail and scheduled for launch in October of 2024, will carry out a detailed study of Europa's ice layer and underground ocean. The spacecraft will carry instruments to analyze the ice and detect signs of water vapor plumes flying near Europa. The Clipper will collect data that will help scientists understand the moon's habitability and potential for life. The surface of Europa is covered by a network of cracks and ridges that indicate its ice layer is active and possibly influenced by the ocean beneath. The Galileo mission found evidence of a magnetic field around Europa, believed to be generated by a conductive saline ocean under the ice. This magnetic field is another piece of evidence supporting the existence of an underground ocean. The potential for life on Europa and Enceladus goes beyond liquid water and organic molecules. These moons also have energy sources that could sustain life, as on Earth. Life thrives in extreme environments where energy comes from chemical reactions rather than from sunlight. Hydrothermal sources in the ocean floors of Europa and Enceladus could provide the energy needed for life. In addition to the Europa Clipper, other future missions are planned to further explore these icy moons. One of these missions is the Enceladus Life Finder, which aims to sample and analyze Enceladus plumes in greater detail. By studying the composition of the plumes, scientists hope to detect signs of life or at least conditions that could sustain it. The search for life on Europa and Enceladus is part of a broader effort to understand the potential for life elsewhere in the solar system and beyond. These moons offer unique environments that could help us answer one of the most profound questions in science. Are we alone in the universe? If life is found on Europa or Enceladus, this would have profound implications for our understanding of biology and the potential for life beyond Earth. It would suggest that life can arise in a variety of environments and that the universe may teem with life in places we have not yet discovered. Uranus, the seventh planet from the Sun, is a fascinating world in our solar system. One of its most unusual characteristics is its extreme axial tilt. Unlike other planets that rotate with their axes more or less perpendicular to their orbital planes, Uranus is tilted at an angle of approximately 98 degrees, which means that Uranus basically rotates around the Sun on its side, with its poles facing the Sun directly in turns. Let's delve into the details of this strange axial tilt and explore the mysteries surrounding it. It is believed that Uranus' strange axial tilt is the result of a colossal impact that occurred billions of years ago, shortly after the planet formed. According to this theory, a massive object, possibly the size of Earth or even larger, collided with Uranus, causing it to tip over. This cataclysmic event would have had a profound impact on Uranus' rotation and orbit, resulting in the extreme tilt we observe today. While this theory is widely accepted, the exact details of the impact and the object involved remain unknown. Some scientists propose that it was not just one impact, but a series of collisions with smaller objects that gradually shifted Uranus' tilt to its current extreme angle. These smaller impacts could cumulatively alter the planet's axis of rotation without necessarily destroying it or significantly changing its overall structure. Uranus' extreme tilt has significant effects on the planet's seasons and climate. On Earth, we experience relatively mild seasonal changes because our planet's axial tilt is only about 235 degrees. However, Uranus' 98 degrees tilt means that each pole receives about 42 years of continuous sunlight, followed by 42 years of darkness, as the planet takes 84 Earth years to complete an orbit. This creates some of the most extreme seasonal variations in the solar system. During the long summer, one pole of Uranus remains under continuous sunlight, while the other side remains in darkness as Uranus continues its orbit. The situation is gradually reversed, and the opposite pole experiences the summer. This unique axial tilt gives rise to extreme temperature fluctuations and unusual climatic patterns. The planet's atmosphere, composed mainly of hydrogen, helium, and methane, presents a dynamic and complex behavior as a result of these extreme seasonal changes. The atmosphere of Uranus is another point of interest. The planet's greenish-blue color comes from the methane in its atmosphere, which absorbs red light and reflects blue and green, giving Uranus its distinctive tone. The atmosphere is also characterized by high-speed winds reaching speeds of up to 560 miles per hour. These winds, along with the planet's axial inclination, create turbulent climatic systems and spectacular cloud formations. One of the most intriguing aspects of the atmosphere of Uranus is the presence of dark spots similar to the Great Red Spot of Jupiter. These dark spots are believed to be storms or vortices, and their appearance may change over time. Observations from the Hubble Space Telescope and other instruments have revealed these characteristics, providing valuable information about Uranus's atmospheric dynamics. The peculiar inclination of Uranus also affects its magnetic field. Unlike Earth, whose magnetic field is approximately aligned with its axis of rotation, the magnetic field of Uranus is inclined at an angle of approximately 59 degrees with respect to its axis of rotation. This misalignment means that the magnetic field is off-center and is more complex than that of Earth. The magnetic field of Uranus is believed to be generated by a layer of ionic mud in the interior of the planet, composed of water, ammonia, and methane. This layer, combined with the planet's rotation, creates the unusual magnetic field. The study of the magnetic field of Uranus provides important clues about the internal structure of the planet. Scientists believe that the core of Uranus is composed of rock and metal, surrounded by a thick layer of icy materials. The outermost layer is composed of gaseous hydrogen and helium, similar to Jupiter and Saturn's composition. Understanding the magnetic field helps researchers develop models of Uranus's interior and its formation history. In addition to its axial inclination and magnetic field, Uranus has a system of rings and moons that add to its unique character. The rings of Uranus were discovered in 1977 and are much darker and narrower than those of Saturn. These rings are mainly composed of large particles and are believed to be relatively young, possibly formed from shattered moon remains or captured objects. Uranus has 27 known moons, the largest being Titania, Oberon, Umbriel, Ariel, and Miranda. These moons are named in honor of characters from the works of William Shakespeare and Alexander Pope. Each moon has its own unique characteristics and geology. For example, Miranda, the innermost of the large moons, has a highly varied surface with deep canyons, ridges, and regions that appear heavily reshaped by geological processes. This diversity suggests a complex history of internal activity and resurfacing. The peculiar characteristics of Uranus have made it a subject of great interest to scientists. However, despite its fascinating characteristics, Uranus has been relatively unexplored. The only spacecraft to have visited Uranus was Voyager 2, which flew by the planet in 1986. Voyager 2 provided valuable data and images, but there is still much to learn about this distant world. Future missions to Uranus could reveal more about its atmosphere, magnetic field, rings, and moons, shedding light on the mysteries of this tilted giant. There is also a hypothesis suggesting the influence of a large moon or multiple moons that exerted gravitational forces strong enough to tilt Uranus. However, the current moons of Uranus are relatively small compared to the planet, making this less likely than the giant impact hypothesis. The study of Uranus also has broader implications for our understanding of the solar system, since by learning more about Uranus, scientists can gain information about the processes that shape planetary formation and evolution. Uranus is considered an ice giant because it has a higher proportion of icy materials compared to the gas giants Jupiter and Saturn. The study of ice giants like Uranus and Neptune can help researchers understand the diversity of planet types and the conditions that lead to their formation. In recent years, there has been growing interest in sending a dedicated mission to Uranus. Such a mission could include an orbiter and possibly a probe to study the planet's atmosphere in detail through long-term observations. Scientists could monitor seasonal changes, atmospheric dynamics, and magnetic field variations. In addition, detailed studies of Uranus's rings and moons could provide new insights into their composition and history. In 1972, an extraordinary spacecraft called Pioneer 10 set off on an exciting mission to explore the asteroid belt and the giant gas planets in the outer solar system. Traveling at 32,000 miles per hour, Pioneer 10 left Earth and paved the way for future missions such as the Voyager probes. The Pioneer 10 mission was very successful, but it had its challenges. The probe carried a hidden problem that baffled scientists for decades, known as the luckiest spacecraft ever launched. Pioneer 10 suffered many malfunctions in the early 1980s while still communicating with Earth. Scientists noticed something strange. Pioneer 10 was slowing down and deviating from its course, as if an unknown force was pushing it toward the sun. For about 15 years, researchers studied and analyzed the data, but could not solve the mystery. The inexplicable deceleration eventually stopped, leaving behind one of the greatest enigmas in spaceflight history. This phenomenon, called the Pioneer anomaly, remains unresolved even today. The flyby anomaly continues to baffle scientists. This failure challenges our understanding of spaceflight and keeps us looking for answers. The Pioneer anomaly is a reminder that, despite our advances in space exploration, there are still mysteries in the universe that test our knowledge and awaken our curiosity. The Pioneer 10 was the innovative NASA mission to explore the outer planets, named thus in honor of the brave pioneers who colonized the west of the United States. The probe aimed to boldly go where no spacecraft had ventured before. The Pioneer 10 reached remarkable milestones, including several firsts in space exploration. It was the first spacecraft to travel beyond Mars, cross the asteroid belt, and reach the gas giant Jupiter. The Pioneer 10 made history by being the first spacecraft to use a fully nuclear energy source and journey beyond our solar system. Although it was destined for a 21-month mission, the Pioneer 10 exceeded expectations and operated for more than 30 years. In January 2003, after a long journey, it sent its last signal back to Earth. Today, the Pioneer 10 continues to drift through space at more than 11,000 miles away, moving in the opposite direction to the movement of the Sun through the galaxy. The Pioneer 11, twin of Pioneer 10, was launched in 1973 and undertook its own journey. Like Pioneer 10, it passed by Mars, navigated the asteroid belt, and reached Jupiter. The Pioneer 11 then made history by becoming the first spacecraft to fly near Saturn. Unlike its twin, Pioneer 11 left Saturn on a different trajectory, exiting the solar system at a 90 degrees angle with respect to Pioneer 10, towards the center of the galaxy, in the direction of the constellation Sagittarius. In 1995, NASA received the last signal from Pioneer 11, which marked the end of its communication. Silently, it disappeared into space, leaving behind a legacy of exploration. Both Pioneer 10 and 11 also left an enigma that has puzzled scientists for decades. Shortly after Pioneer 10 and 11 ventured beyond Jupiter and Saturn, their navigators noticed something strange. Both spacecraft were slowing down more than expected, as if an unknown force was gently pulling them towards the Sun. While some acceleration was expected due to the Sun's gravity, the data showed an excessive deceleration that could not be easily explained. The deceleration was very small, only 1/10,000,000th of Earth's gravitational acceleration. In 1998, John Anderson, of the JPL, and his colleagues calculated that the spacecraft were slowing at a rate of about 300 inches per day. This small difference had significant implications. The Pioneers ended up thousands of kilometers closer to Earth each year than expected, and ended up staying at distances from their planned locations similar to the separation between the Earth and the Moon. Year after year, the spacecraft deviated by a few thousand kilometers from their planned positions. At first, this did not raise many concerns, but as time went on, it became clear that this small deceleration persisted as the spacecraft ventured further into space. The Pioneer anomaly remains one of the greatest mysteries of space exploration, challenging our understanding and arousing curiosity about the forces acting in the cosmos. This mystery adds to the many questions we have about the universe, which pushes us to seek answers and continue exploring. The question of how the universe began from nothing is one of the most interesting in cosmology. One of the main theories of modern cosmology is the Big Bang theory, which explains how our universe began and evolved. Imagine all the stars, planets, and galaxies compressed into an incredibly hot and dense point. Scientists believe that this is how everything began about 138 billion years ago. Since then, the universe has been expanding, and cooling. This small point exploded in an event called the Big Bang, and from that moment, the universe began to grow and cool. The term Big Bang can be somewhat misleading, as it suggests an explosion in space. However, the Big Bang was not an explosion in space, but an expansion of space itself. In the first fractions of a second after the Big Bang, the universe expanded exponentially in a period known as cosmic inflation. During this time, the universe grew from an almost infinitesimal point to a macroscopic scale. As the universe expanded, it cooled, allowing energy to transform into particles of matter. These particles combined to form simple elements, such as hydrogen and helium. For billions of years, these elements merged under the force of gravity to form stars, galaxies, and planets. These elements were formed in the first minutes after the Big Bang, when the universe cooled enough for protons and neutrons to form nuclei. But how do we know the Big Bang happened? The Big Bang theory is supported by much evidence. A key piece is the cosmic background radiation, a residual glow from the early universe. This radiation gives us a picture of the universe only 300,000 years after the Big Bang. Before that, the universe was so hot and dense that we could not take pictures of it. This radiation was discovered by chance in 1965 by Arno Penzias and Robert Wilson. The uniformity and slight fluctuations of the radiation support the idea of cosmic inflation and the rapid expansion of the universe. Another piece of evidence is the redshift of galaxies, which means that galaxies are moving away from us, showing that the universe is expanding and growing. This was first observed by Edwin Hubble in the 1920s. The further away a galaxy is, the faster it seems to move away from us, which supports the idea that the universe was once much smaller, hotter, and denser. But the Big Bang theory also raises some big questions. For example, it does not explain what happened before the Big Bang or what is beyond the part of the universe that we can see. It also introduces the idea of cosmic inflation, which is a rapid expansion that occurred soon after the Big Bang. Before the discovery of cosmic microwave background radiation, a popular idea known as the steady-state theory existed. This theory suggested that the universe has no beginning or end, but remains the same as a whole, although it expands by constantly creating new matter. This theory was popular in the 1940s, but lost support when scientists discovered the cosmic background radiation in 1965, which strongly supports the Big Bang theory. In addition, theories such as the cyclic model, which suggests that the universe undergoes endless cycles of expansion and contraction after the Big Bang. The universe expanded and cooled. At the beginning, it was a hot, dense soup of particles that, as it expanded, cooled and allowed the particles to come together to form the first atoms. These atoms formed the first stars and galaxies. The expansion of the universe continues today, with galaxies moving away from us in all directions. Let's think even further back. The first particles of any kind that existed were protons and neutrons, which together form the nucleus of an atom. These appeared about 1/100,000th of a second after the Big Bang. Before that, there really was no material as we know it, but physics allows us to go back even further in time to processes that took place before any stable matter existed to understand how the universe could begin from nothing. We have to explore the strange world of quantum mechanics. In the realm of quantum physics, nothing is not the absence of something, but rather a state of vacuum energy in which particles constantly appear and then disappear. This phenomenon is known as quantum fluctuations. Quantum fluctuations occur in what is known as a quantum vacuum, a state with the lowest possible energy in which particles can momentarily appear and then disappear according to the laws of quantum mechanics. It is possible that these fluctuations can lead to the creation of a universe. In this context, nothing is an energetic state that can give rise to matter and energy. One of the key concepts for understanding this process is the Heisenberg uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be known with arbitrary precision. This principle allows the temporary creation of particles from the vacuum, as long as they disappear quickly enough to comply with the law of conservation of energy. Quantum fluctuations can cause particles to appear and then disappear shortly thereafter. This may sound strange, but such particles have been observed in many experiments. The vacuum of space is full of particles that are constantly created and destroyed, apparently from nothing. This suggests that the quantum vacuum is actually something rather than nothing. Where did space-time itself come from? To answer this, we have to go back to the very beginning, to the Planck era. This period was so early in the history of the universe that our best theories of physics no longer work. It occurred only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Normally, physicists use quantum mechanics for tiny particles and general relativity for large cosmic scales. But to understand the Planck era, we need a complete theory of quantum gravity that combines both. We still don't have a perfect theory of quantum gravity, but there are ideas like string theory and loop quantum gravity. These theories suggest that ordinary space and time come from deeper microscopic processes. What we experience as space and time is the result of quantum processes, which are difficult for us to understand because we're used to the large scale. Quantum fluctuations occur constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a brief instant, and then destroy each other. This phenomenon is known as quantum foam, but quantum fluctuations alone do not explain the enormous scale and complexity of the universe. There is dark energy, a mysterious force that fills all space and accelerates the expansion of the universe. Although we do not fully understand dark energy, it is believed to play a crucial role in the creation and evolution of the cosmos. So how do we get from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded exponentially in the Planck era, setting the stage for the formation of galaxies, stars, and planets. Our usual understanding of space, time, and cause and effect falls apart despite all this. Candidate theories of quantum gravity describe something physical that occurs in the Planck era, some quantum precursor to ordinary space and time. But where did that come from? Even if causality does not work in the usual way, it could still be possible to explain parts of the universe from the Planck era in terms of other parts. Unfortunately, our best physics still cannot provide clear answers. Until we develop a theory of everything, we will not be able to give a definitive answer. The most we can say with confidence is that physics has not found any confirmed case of something arising from music, nothing. When we look around, everything we see is made of matter. Everything we touch, see, and interact with is made up of tiny particles. For billions of years, these particles have come together to form galaxies and stars. They all follow the same physical laws and exist within the same space-time framework. But there was a time when the universe had nothing. So where did all this matter come from? Although it may seem that everything came from something, scientists also consider the possibility that everything came from nothing. But what does nothing mean in science? To truly answer the question of how something could arise from nothing, we would first need to understand several interpretations of nothing. This is the state in which there is nothing, in which the essential components of everything we see are absent. Imagine a universe without galaxies, stars, planets, or even human beings. Everything we know and interact with is composed of tiny subatomic particles. These particles are components that shape our universe. If we start with a universe full of matter, we can understand how it grows, cools, and is influenced by gravity to become the universe we see. Nowadays, we know that stars go through life cycles, creating heavier elements that give rise to the birth of new stars, planets, organic compounds, and finally, life. But here are some big scientific questions. how do we end up with a universe dominated by matter, not one with equal amounts of matter and antimatter? This is one of physics' greatest mysteries. The universe is composed almost entirely of matter, with barely any antimatter. All the stars, planets, and galaxies we have observed are made of matter. So, how do we get this matter surplus? This enigma is known as the barrier of Genesis, the process of creation of an excess of boranos over the antiboranos in the early universe. Scientists have many theories, but we still do not have a definitive answer. We do not know why there is more matter than antimatter instead of an equal balance. To truly answer how something could arise from nothing, we need to understand different ideas of what nothing means. Our second interpretation of nothing is the emptiness of vast space. Perhaps you think nothing is really having nothing at all. If that is the case, then the first explanation of nothing with missing building blocks does not quite fit, because it still implies something. Something. To really understand this concept of nothing, let's imagine we get rid of all the basic elements of matter, which means eliminating every particle and every bit of energy. If we could eliminate all this, what would remain? Only the vast expanse of empty space, without particles, without matter, without any radiation. This is what some scientists consider the true scientific meaning of nothing. Space-time itself, guided by the principles of general relativity. The speed of light continues to exist, and the gravitational constant retains its values. And, more importantly, there is something called zero-point energy. Even in the emptiest space, there is still a small amount of energy that today we see as dark energy, which is driving the expansion of the universe. But even in this extremely empty scenario, some fundamental aspects still exist. The laws of physics are still there. Quantum fields, such as the electromagnetic field, the gravitational field, the Higgs field, and the fields related to nuclear forces, still exist. So, even without matter or radiation, this version of nothing still gives rise to an intriguing universe. This leads us to the idea of a universe arising from nothing. It is fascinating to think that, even in the absence of everything we see, the universe can still be a dynamic and captivating place. The third interpretation of nothing for scientists is the idea of nothing as the lowest possible energy state. At this moment, our universe has something called zero-point energy, which is a small amount of energy that exists everywhere in space. We do not know if this zero-point energy is the lowest possible energy, or if there is an even lower energy state that we have not yet discovered. There is the possibility that we are in a false vacuum state, with a true vacuum or the absolute lowest energy state, either close to zero or even reaching or exceeding it. If the universe passed from this false vacuum to a true vacuum, it could trigger a catastrophic event called vacuum decay. This would drastically change the universe. Photons, which are particles of light, would acquire mass. The electromagnetic force would be confined to short distances, and most of the sunlight coming from the sun would not reach Earth. Thinking of nothing as the lowest energy state. Imagine an energy state in which all matter, energy, radiation, and any distortion in space-time are eliminated. What remains is a state of perfect vacuum, but with the laws of physics still in force. This minimum energy state would make it impossible to create any kind of work, energy, or particles from it. However, some might still see this as something, since space-time and the laws of physics would still exist in this state. There would still be a backdrop for events to occur, but without actors or actions, it would be like a play without characters, plot, or setting, just an empty stage. Now, imagine reaching the true, fundamental state of the universe, whatever it may be. In this state, all matter, energy, and any distortion in space-time would be eliminated. What would remain is the ultimate material vacuum. This minimum energy state would make it impossible to create any kind of work, energy, or particles from it. However, some might still see this as something, since space-time and the laws of physics would still exist. So our third interpretation of nothing is the lowest possible energy state for the universe. Even in this state, the structure of space-time and the laws of physics remain. It is another incredible mystery that keeps scientists exploring and searching for answers. This is the most extreme interpretation of nothing. The idea that true nothing only occurs when the entire universe and its governing laws disappear completely. This is a radical idea that goes beyond our usual understanding of reality. Imagine getting rid of everything, including space-time and even the laws of physics. This type of nothing is beyond what we can define with physics, because it represents an absolute vacuum, a total absence of everything from a physics point of view. This idea is challenging. How can something like space-time exist if there is no space or time? How can the laws of physics work if there is no framework for them? This type of nothing is hard to grasp and may not have meaning in the real world. Thinking about this absolute nothing raises questions without clear answers. For example, how could space and time begin where they do not exist? Is it possible to have something without space or begin without time? Imagine nothing, a complete void from physics' point of view. It suggests a state beyond the limits of space and time, from which our universe and its laws could emerge. However, we're not sure whether this idea makes sense or is just a product of our imagination. This concept poses many difficult questions. For example, how can space and time begin in a place or moment where neither exists? Can we even imagine something that exists outside the universe, without space, or that begins without time? Where would the rules governing particles and their interactions come from? This idea of nothing, although it seems philosophically complete, might not have any real substance. It could just be a way of understanding things that are beyond our reality. When scientists talk about nothing, they often assume that everyone has the same idea of what it means, but that is not always so. Different people and contexts can change our understanding of nothing, while theories about nothing are based on scientific principles and observations. The study of cosmic background radiation, the faint glow of the Big Bang, provides information about the conditions of the early universe. Detailed measurements of a CMB have helped us understand the age, composition, and structure of the universe. Observations of the expansion of the universe, as described by Hubble's law, support the idea that the universe began from a dense and hot state. In addition, the discovery of dark matter and dark energy, which constitute most of the mass and energy content of the universe, suggests that our understanding of the universe is still incomplete. The phrase something from nothing could mean creating something completely new where nothing was before, but not everyone agrees on what nothing really means. In the end, it is important to understand which version of nothing someone refers to in everyday language. Nothing suggests the absence of anything. However, in the context of cosmology, nothing can be much more complex, as it can refer to a quantum vacuum, a state with the lowest possible energy in which particles and antiparticles constantly appear and disappear due to quantum fluctuations. Philosophically, nothing can be even more abstract. Some philosophers argue that true nothing is an absolute void without property. Others suggest that, even in a state of nothing, there must be some form of potentiality or possibility allowing the appearance of something. None of the evidence from cosmic microwave background radiation or quantum fluctuations tell us about what was before the Big Bang. One of the most mysterious questions of cosmology is what existed before the Big Bang and what created the singularity that led to it. The Big Bang theory tells us that the universe began from a singularity. Think of a singularity as a point where everything we know about space and time falls apart, including laws of physics. If our usual laws of physics do not apply, what rules can explain this? Let's begin with the ideas of Albert Einstein. His theory of relativity changed our view of the universe by linking mass and time. According to his theory, time is not fixed, but changes depending on the gravitational fields of objects of significant mass. He showed that massive objects like Earth can slow time. Now, if mass slows down time, imagine what the singularity, which contains all the mass of the universe, would do. It would stop time completely. Therefore, according to Einstein, the idea of what was before the Big Bang does not make sense, because time itself did not exist. Cosmic microwave radiation, cosmic background radiation, is a key piece of evidence, as it comes from a time approximately 380,000 years after the Big Bang, when the universe was cooling and forming hydrogen atoms. Before this, the universe went through several phases, from the Planck era to the Great Inflationary Unification, the Electroweak epoch, the Quark epoch, and the Hadron epoch. In each phase, different particles and forces were observed that evolved into what we know today. When we talk about the universe on such a small scale, quantum mechanics replaces classical physics. This led scientists like Stephen Hawking to think about how quantum theory could apply to the entire universe. This is where inflationary quantum cosmology comes in, unlike classical theories that describe the singularity as a point with zero volume. Quantum cosmology suggests that there is an element of uncertainty, which means that we cannot determine the exact moment when the universe was created, and particles can appear and disappear from existence from what we call vacuum. In physics, a vacuum is not a state of absolute emptiness, but rather a state without particles. According to Heisenberg's uncertainty principle, there's always some level of fluctuation. So a perfect vacuum with zero field values is music impossible. This may sound strange, but Einstein's famous equation, E equals mc squared, helps to explain it. The positive energy of stars and galaxies must be balanced by an equal amount of negative energy, such as gravity. If the total energy of the universe is zero, then it may come from nothing. The idea that hundreds of billions of galaxies can come from nothing sounds incredible. However, Einstein's famous equation gives us clues. According to this equation, all the positive energy of stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which appears as gravity in a closed universe or one that will expand. E equals mc squared gives us some clues. According to this equation, all the positive energy of stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which appears as gravity in a closed universe, or that will eventually collapse on itself. These positive and negative energies would cancel each other out perfectly, resulting in a net energy of zero for the universe as a whole. Stephen Hawking wondered how a universe with zero total energy could arise from nothing at all. He suggested that gravity's negative energy could balance the positive energy needed to create matter. This makes empty space stable. The physicist Alexander Vilenkin took this idea further, demonstrating that a small vacuum full of energy could spontaneously appear from nothing and expand into the universe we see today. This means that our universe could have started from nothing, a state in which time did not exist. Another intriguing possibility is the multiverse hypothesis, suggesting that our universe is only one of many universes existing simultaneously. In this framework, the Big Bang that created our universe could be just one of countless events occurring within a larger multiverse. In the multiverse scenario, new universes could be constantly created, each with its own set of physical laws and constants. These universes could be born from different processes, like collisions between higher dimensional membranes in string theory. The existence of a multiverse implies that our universe's beginning was only an event in an endless cycle of creation and destruction. Some theories of physics propose the existence of higher dimensions beyond the three spatial dimensions and the temporal dimension with which we are familiar. These higher dimensions could play a key role in the universe's origin. String theory, for example, suggests that the universe's fundamental components are one-dimensional strings vibrating in multiple dimensions. In this framework, our universe could be a three-dimensional brain floating in a higher dimensional space. Collisions or interactions between these brains could trigger events like the Big Bang, creating new universes. So what was there before the Big Bang? The theories we've explored suggest that time itself began with the Big Bang, making before a complicated concept from singularities to quantum fluctuations. These ideas show how incredible and mysterious our universe truly is. The Big Bang Theory explains how the universe expanded from super hot and dense state, but doesn't tell us what happened before that moment. According to the theory, time, space, matter, and energy began with the Big Bang. However, Some scientists have ideas about what may have existed before the Big Music Bang. An interesting idea is the Big Bounce. This theory suggests that the universe goes through cycles of expansion and contraction, so the Big Bang we know could have been just one of many bounces, with the universe constantly being reborn. Another fascinating idea is the multiverse concept. This theory proposes that our universe is only one of many universes, each having its own set of physical laws. In this model, what existed before our Big Bang could have been another, completely different universe. These ideas exceed the limits of our current knowledge and delve into the realm of speculation, since they are based on advanced concepts of quantum physics and in the still theoretical field of quantum gravity. Scientists are trying to connect quantum mechanics and general relativity to better understand these possibilities. After the Big Bang, the universe continued expanding and cooling. At first, it was just a soup of tiny particles, but as it cooled, these particles came together to form the first atoms, mainly hydrogen and helium. While these theories offer exciting visions of what may have been before the Big Bang, they remain largely theoretical, highlighting the profound mystery of our universe's origins. By looking back in time, we can explore the origins of each cosmic structure. Each discovery leads to another question: where did this come from, and how was it formed? These questions continue until we reach a point where the only honest answer is that we do not know, at least not yet with our current understanding. Then we are faced with intriguing questions. How did all this come to be the life we see today? Life is possible thanks to complex molecules that originally evolved from the simple atoms listed on the periodic table. These atoms are the fundamental components of all ordinary matter in our universe. These atoms were not simply there from the beginning of the universe, but were formed through numerous cycles of stars that are born, live, and then die. Each stellar life cycle contributed to the nuclear reactions that produced these atoms, which were then recycled into new generations of stars. Without this continuous process, the creation of planets and the complex chemistry necessary for life would not be possible. To understand how the stars and galaxies we see today came to be, some key pieces must first fit together. Gravity plays a huge role. It attracts smaller groups of stars and galaxies to form the large galaxies we observe, starting new rounds of star formation. For gravity to do its job, there must be enough mass already grouped into masses. This is where dark matter comes into play. Early in the universe's history, dark matter formed halos that helped prevent newly formed stars from scattering their material back into space. In addition to the right mix of matter, such as atoms, dark matter, and radiation, it is crucial that this mix not only produce the cosmic microwave background, a kind of residual glow from the Big Bang, but also created the light elements during that hot and dense state of the early universe. The growth of galaxies and star clusters depended on small initial differences in density, often called seed fluctuations, which needed to grow under gravity's influence. Finally, there must be processes that initially created these density variations, dark matter, and the first batches of ordinary matter. To understand how our universe emerged from the chaos of the Big Bang, we must consider some critical conditions from the beginning. On the one hand, the laws of physics, the structure of space-time, and the essence of matter and energy were not simply there, but had to arise somehow. As it expanded, it cooled, and eventually stars and galaxies began to form. This understanding helped develop what we now call the Big Bang Theory. Scientists believe that everything began about 138 billion years ago, and it is currently our best explanation of how our universe began. When we use telescopes to look beyond the first stars, we see a special type of light that is not the light of the stars, but the light that remains from the Big Bang and forms a kind of background glow. Beyond where the stars are, however, the Big Bang Theory raises a new question. It suggests that the universe used to be much brighter, especially during a time called the era of recombination. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow from the Big Bang, known as cosmic background radiation, should be very bright. According to Olber's paradox, this bright background should make it difficult for us to see faint stars in the current night sky. Most scientists agree that the universe is about 138 billion years old. When we look at light that is 13,800 million years old, we do not see stars, not because the light has not reached us, but because we're looking back to a time before the existence of the stars existed. The further we look into space, the further back in time we are seeing, until we reach what looks like the edge of the universe. This is not a real edge, but the oldest light we can see, known as the cosmic microwave background. It is the residual glow of the Big Bang. Since the Big Bang occurred 138 billion years ago, the universe has followed three main rules as it grows and changes. First, in the beginning, the universe was extremely small, very dense, and super hot. Second, only a fraction of a second after it began, the universe began to grow and cool. Third, and this is really important, the universe will continue to expand and cool. Astronomers believe that this will continue until the universe becomes so cold that all heat disappears. They call this the thermal death of the universe, sometimes also known as the Great Freeze. In this future scenario, the universe has expanded so much that it has completely cooled and all thermal energy has disappeared. All these rules show us that our universe has been getting bigger for the last 138 billion years. When the universe began, it was full of very bright and hot light. As the universe has expanded, this light has stretched. This stretching has converted the light into longer wavelengths, which means it is colder and not as bright as before. This is what we call the redshift effect. It is the reason why cosmic background radiation is not extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expansion of the universe solve Olber's paradox. The universe began from a single point and grew rapidly during the Big Bang over billions of years has cooled because the universe is not infinitely old. There's a limit to how far we can see into space. The redshift effect also makes the light from distant objects appear fainter. These combined factors give us the dark sky we see today. The fact that the night sky is dark shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe began with the Big Bang and has been expanding ever since. The night sky is like a quiet reminder of how the universe began as a very hot and dense place. This idea helps solve Olber's paradox and also makes us appreciate how incredible and complex the universe really is. The question of the age of the universe is fundamental in cosmology and astronomy. The most accepted explanation about the origin of the universe is the Big Bang theory. According to this theory, the universe began as an incredibly hot and dense point approximately 138 billion years ago. This singularity contained all the matter and energy that would eventually form everything we see today. The universe has been expanding ever since, cooling and forming structures such as galaxies, stars, and planets. To determine the age of the universe, scientists use various methods, including the study of cosmic microwave background radiation, the observation of the rate of expansion of the universe, and the analysis of the oldest known objects within the universe. One of the most important tests to determine the age of the universe is the CMB, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is the residual glow of the Big Bang. It is the residual heat of the early universe, now cooled and stretched to microwave wavelengths. Because the universe is expanding, the European Space Agency's Planck satellite has provided the most accurate measurements of the CMB to date. Planck's data has allowed scientists to determine that the age of the universe is approximately 138 billion years. The CMB offers us a perfect picture of the universe when it was only 380,000 years old. By studying small variations in the CMB, scientists can learn about the initial conditions of the universe and how it evolved. These variations tell us about the distribution of matter and energy in the early universe, which helps us estimate its age. Another method to determine the age of the universe is to observe its expansion. In the 1920s, astronomer Edwin Hubble discovered that galaxies are moving away from us. The further away a galaxy is, the faster it appears to move. This relationship is known as Hubble's law. By measuring the Hubble constant, scientists can estimate the time since the Big Bang, giving us an estimate of the age of the universe. The Hubble constant measures the rate at which the universe expands. By determining the Hubble constant, scientists can estimate how long the universe has expanded since the Big Bang. This implies measuring the redshift of distant galaxies and the distances to these galaxies using various methods, such as the observation of SE variable stars and supernovas. However, determining the precise value of the Hubble constant has been a challenge. The different measurement methods have yielded slightly different values, leading to what is known as the Hubble tension. Despite this discrepancy, the average value of the Hubble constant, combined with other cosmological data, suggests that the age of the universe is around 138 billion years. Over the years, different methods have been used to measure the Hubble constant, including observations of Cepheid stars and the study of the CMB. These methods have consistently supported the Big Bang theory and our estimate of the age of the universe. Stars also provide valuable clues to the age of the universe. By studying the light cycles of stars, scientists can estimate the ages of the oldest star clusters. An important type of star cluster for this purpose is globular clusters. White dwarf stars, which are the remains of stars that have exhausted their nuclear fuel, also provide valuable age estimates by analyzing the cooling rates of white dwarf stars in globular clusters. By analyzing the light from these stars and comparing it with models of stellar evolution, scientists can determine how long these stars have been cooling, and therefore their ages. Since globular clusters formed shortly after the Big Bang, scientists can estimate their age. These ages provide a lower limit for the age of the universe. The oldest globular clusters and white dwarf stars have been found to be around 13 billion years old. Since these objects must have formed after the Big Bang, their ages provide a lower limit for the age of the universe, which supports the estimate of 138 billion years. Another method for determining the age of the universe involves the radioactive decay of certain elements, such as uranium and thorium. The decay occurs at known rates, so measuring the proportions of these elements in old stars and meteorites allows scientists to estimate the time since these elements formed. This technique, called radioactive dating, has provided age estimates consistent with other methods, supporting the idea that the universe is around 138 billion years old. Gravitational waves are ripples in space-time caused by violent events. They offer another way to study the history of the universe. First detected in 2015 by the LIGO and Virgo observatories, gravitational waves provide a new way to measure the Hubble constant and the age of the universe. By observing the mergers of neutron stars and black holes, scientists can use gravitational waves to estimate the distances and expansion rate of the universe. This new field of gravitational cosmology promises to provide even more accurate estimates of the age of the universe. According to general relativity, our universe has specific characteristics. It is uniformly dense on a large scale, it has consistent laws and properties, and the Big Bang occurred everywhere simultaneously. These characteristics create a unique link between the age of the universe and its expansion history. To determine it, we rely on various observations, including direct measurements of the brightness and distance of celestial objects, which help us build the cosmic distance ladder. We also use observations of large-scale structures, clusters of galaxies, and baryon acoustic oscillations, as well as fluctuations in the cosmic microwave background, which offers a snapshot of the universe when it was only 380,000 years old. To summarize the age of the universe, scientists use various methods, including studying the cosmic microwave background, observing the redshifts of distant galaxies, analyzing the life cycles of stars and globular clusters, and exploring the effects of dark matter and dark energy. Each method provides valuable information, and together, they give us a detailed understanding of the age and evolution of the universe. For years, human beings have wondered about the shape of the Earth. Is it flat, round, rectangular, or like a saddle? Today we know that the Earth is approximately a sphere, but have you ever thought about the shape of the universe? Scientists have discovered that the universe expands infinitely and does not stop. but its shape remains a matter of debate. There are three possible shapes: flat like a sheet of paper, closed like a sphere, or open like a saddle. These shapes are not just theoretical ideas. They have significant implications for the future of the universe. They can tell us a lot about its past and what might happen in the future. Will the universe continue to expand forever, begin to contract, or is it infinite and without limit? Let's explore what these different shapes mean for the destiny of the cosmos. The general shape of the universe depends on two main factors: its density and its expansion rate. So, is the universe closed, open, or flat? Approximately 2/3 of the universe is composed of dark energy, and just over a quarter is dark matter. The rest is normal matter that we know, such as stars and planets. When scientists talk about the density of the universe, they are referring to how much matter and energy exists in a given space. If the universe has enough density for gravity to balance its expansion, it will take on a spherical shape, known as a closed universe. A closed universe would be finite, but without limits, meaning that one could travel endlessly without ever reaching an edge. On the other hand, if the universe does not have enough density to stop its expansion, it will be shaped like a saddle, known as an open universe. However, the most reliable scientific data suggests that the universe is flat. In a flat universe, the density is adequate, allowing it to expand in all directions without any curvature. What do we mean when we say that the universe is flat? This flatness isn't like a two-dimensional surface that we see every day. Imagine you are in a corner of a square room. Walk 3 meters to the next corner along the wall, then turn 90 degrees, walk another 3 meters, turn another 90 degrees, and do this 2 more times. You will end up back where you started, forming a square. This follows the Euclidean geometry that we learned in school. Now, if you add one dimension to this concept, you will get a flat universe. In a flat universe, geometry follows the rules of Euclidean geometry. This means that parallel lines never intersect, and the angles of a triangle add up to 180 degrees. A flat universe can be visualized as a two-dimensional plane extending infinitely in all directions. A flat universe suggests that the density of matter and energy is equal to the exact critical density. The critical density is the amount of matter and energy needed for a flat universe. Now let's consider a universe with positive, or closed, curvature. Imagine you start at Earth's equator and walk toward the North Pole. If you turn 90 degrees and walk back to the equator, turn another 90 degrees and return to the starting point, you will notice that in a closed universe you would only need to turn 3 times instead of 4. To simplify it more, imagine 2 rockets flying side by side in a flat universe. They would remain parallel forever. In a closed universe, their paths would curve and meet again. In an open universe, they would move away and never meet again. An important clue about the shape of the universe comes from the cosmic microwave background, the residual heat from the Big Bang. Scientists have studied the temperature variations in the CMB and have found almost no curvature to support the idea of a flat universe. However, in 2019, a study suggested that CMB measurements might indicate a closed universe. This was based on the curvature of CMB light caused by gravity. The amount of curvature observed was greater than expected, and a closed universe could explain this, but the team that performed the measurements did not consider this to be important. Some experts believe that it could simply be a random anomaly in data. Even so, these findings are worth mentioning, since, although they do not directly prove that the universe is closed, they suggest that something important might be happening. Some researchers even call it a cosmological crisis. If the universe were closed, it would conflict with other data, making it difficult to accept if it were proven to be true. The idea of a closed universe would overturn years of consolidated research. However, there is no other evidence that challenges the prevailing view that the universe is flat. Other CMB measurements and telescope data support a flat universe. Additional data, such as patterns left in galaxies by ancient sound waves, also support the flatness hypothesis. Given the overwhelming evidence in favor of a flat universe, most scientists are skeptical of a single contradictory finding. While the study suggesting a closed universe is interesting, other data consistently support a flat universe. Recent research combining multiple data sets found no deviations from flatness, suggesting that the observed anomaly could be a statistical fluctuation. Other studies have reached similar conclusions, indicating that there is no need to revise the current cosmological model now. It seems that the universe behaves like a three-dimensional sheet of paper, although not everyone is completely convinced that it is definitely flat. That is how it seems. Based on current observations, it is important to remember that our view is limited to the observable universe, so there may be aspects that we are unaware of. If the universe has curvature, it would have to be so immense that the 93,000 million light-years that we can observe are not enough to detect it. To make an analogy, it is like being in a field with fog and only being able to see a small flat area, while the true shape of the terrain remains hidden beyond the fog. When we say that the universe is flat, we mean that the part that we can observe looks like a flat, three-dimensional space. Music. The most widely accepted explanation of the origin of the universe is the Big Bang theory. According to this theory, the universe began approximately 138 billion years ago from an incredibly hot and dense state, often described as a singularity. This singularity expanded rapidly, giving rise to the universe as we know it. One of the fundamental aspects of the Big Bang theory is that the expansion of the universe is uniform and isotropic, which means that it looks the same in all directions and does not have a preferred center. This expansion is often compared to the surface of an inflating balloon, where each point on the surface moves away from all other points. Just as there is no center on the surface of a balloon, scientists believe that there is no central point in the universe from which everything expands. To understand why the universe has no center, we must consider the cosmological principle. This principle states that the universe is homogeneous and isotropic on a large scale. Homogeneity means that the universe has the same composition and properties everywhere, while isotropy means that the universe looks the same in all directions. The cosmological principle implies that there is no special location in the universe that can be considered its center. Instead, each point in the universe can be seen as the center of its own observable universe. This principle is supported by observations of cosmic microwave background radiation, which show a uniform and isotropic distribution of radiation left over from the Big Bang. When we talk about the universe, it is important to differentiate between the observable universe and the complete universe. The observable universe is the region of the universe that we can see from Earth, limited by the speed of light and the age of the universe. Since light takes time to travel, we can only observe objects whose light has had time to reach us since the Big Bang. The observable universe has finite size, with a radius around 46,500 million light-years. However, this does not imply a center in the usual sense. The observable universe is centered on the observer, which means that each point of the universe has its own observable universe centered around it. The expansion of the universe is not like an explosion from a central point into a pre-existing space, but rather it is the expansion of space itself. This concept is described by the metric expansion of space, where distances between points in the universe increase over time. This expansion is uniform and occurs simultaneously everywhere. A useful analogy is to imagine raisin bread. As the dough expands, the raisins move from each other. There is no single center of expansion within the dough, but each raisin sees the others moving away. Similarly, in the universe, each galaxy sees other galaxies moving away due to space's expansion. One of the key proofs of the expansion of the universe is the redshift in light from distant galaxies. As the universe expands, light from distant galaxies stretches, causing it to shift toward the red end of the spectrum. This redshift is proportional to the distance of the galaxy, which means that the more distant galaxies are moving away faster. The observation of redshift by Edwin Hubble in the 1920s provided strong evidence for the expansion of the universe and helped establish the Big Bang theory. The uniformity of redshift measurements supports the idea that expansion is isotropic and that there is no central point from which the universe expands. Current cosmological models suggest the universe is infinite and unbounded, or finite but unbounded. An infinite universe extends infinitely in all directions, while a finite but unbounded universe is closed and has no edges, much like the surface of a sphere. In any case, there is no central point or edge to the universe. If the universe is infinite, each point within it is essentially the center of its own observable universe. If the universe is finite but unbounded, traveling in one direction long enough would take you back to your starting point, similar to the circumnavigation of the Earth. The concept of a universe without a center challenges our intuitive understanding of space and location. Throughout history, human beings have often sought a central point or privileged position in the cosmos. The shift to a heliocentric model of the solar system during the Renaissance was a significant step in changing this perspective. The understanding that our galaxy is one among billions in an expanding universe further decentralizes our place in the cosmos. Philosophically, the lack of a center in the universe emphasizes the idea of an interconnected and uniform cosmos. It suggests that no place is more significant than another, aligning with the cosmological principle of isotropy and homogeneity. Some theories of modern cosmology propose the existence of a multiverse, a collection of multiple universes existing simultaneously. In the multiverse scenario, our universe is just one of many, each with its own laws and constants of physics. If the multiverse exists, the concept of center becomes even more abstract, as there would be no central point in the multiverse as a whole. To answer the question of what exists outside the edge of the universe, it is important to first differentiate between the observable universe and the complete universe. The observable universe is the region of the universe that we can see from Earth, limited by both the speed of light and the universe's age. Because light takes time to travel, we can only observe objects whose light has had time to reach us since the Big Bang, approximately 138 billion years ago. Cosmologists estimate that the oldest photons we can observe have traveled between 45,000 and 47,000 million light-years since the Big Bang, meaning the observable universe has a radius of about 46,500 million light-years. This is due to the expansion of the universe, which has caused distant objects to move away from us, making the observable universe much larger than 138 billion light-years. In addition, it has been concluded that the diameter of the observable universe is about 93,000 million light-years, more or less. This observable universe includes everything we can see, from the smallest particles, such as quarks, to the largest structures, such as quasars, stars, planets, nebulae, and black holes. It is important to note that the observable universe is limited to the light that has reached us. The concept of edge of the universe usually refers to the limit of the observable universe. However, this edge is not a physical boundary, but the limit of what we can study or see. Beyond this observable limit, the universe continues to exist, but we cannot observe it directly because light from those regions has not yet reached us. The universe is believed to be much larger than the observable part and possibly infinite. If the universe is infinite, it extends endlessly beyond the observable edge. In this case, asking what exists outside the edge of the universe is meaningless because there is no edge, just more universe. But how can the observable universe have 93,000 million light-years in diameter if the universe itself is only about 13,800 million years old? This apparent contradiction is resolved by understanding a fundamental concept of physics. According to the theory of special relativity, objects close to each other cannot exceed the speed of light between each other. However, this limit does not apply to distant objects, especially when the space between them is expanding. It is not that these objects are moving through space faster than light, but that space itself is expanding, causing them to move away from each other at high speeds. To reach the edge of the observable universe, it would be necessary to exceed the speed of light, a feat considered impossible by most physicists, or to find a way to circumvent the limitations of space-time, perhaps through theoretical constructs such as wormholes or warp drives, although they are also considered highly speculative. According to the concept of cosmic inflation, the universe could be at least 10 to the 23rd power times larger than what we can observe. What lies beyond the observable universe remains a mystery, as it lies beyond our ability to observe. Nevertheless, various theories speculate about what could exist in these unexplored regions. The first theory is simple, but surprising. Astronomers think that the space beyond what we can see could simply be a continuous extension of cosmic characteristics similar to our observable universe. It makes sense to assume that the universe beyond our sight would not be very different from what we can observe. It is difficult to imagine a universe that simply ends abruptly, as if there were a giant wall that marked its limit. So the idea that the universe could be infinite is natural. But infinite means that beyond what we see, there could be infinite stars, planets, and even all the possible scenarios you can imagine. If the universe is truly infinite, following this idea to its ultimate consequences, it means that somewhere out there, there could be another person who looks exactly like you and lives a life very similar to yours. There could also be versions of you that are slightly different. Maybe one is a little shorter, another could have died a few years ago, or one could be missing a finger. It is possible that this other version of you is watching this video right now, maybe even picking your nose like you would be doing. It's a crazy idea, but that's how the concept of infinity works. Another theory called dark flow emerged in 2008 when astronomers observed clusters of galaxies moving in the same direction at an incredible speed, more than 2 million miles per hour. This could be caused by huge, unknown structures beyond what we can see that attract these galaxies with their gravity. These structures could be huge clusters of matter and energy or unusual distortions of space-time that could even connect to other universes. We really don't know what these massive entities could be, although some studies have tried to disprove the dark flow theory, which is still a subject of debate. There's also the idea of a multiverse in which our universe is just one bubble in a huge sea of other universes. This theory suggests that these universes can interact and that the gravitational attraction between them could cause collisions that would lead to events similar to our own Big Bang. These ideas are just some of the popular theories about what could be beyond the part of the universe that we can see. The true nature of what is out there remains one of the greatest mysteries of cosmology, which drives continuous research and discovery to learn more about our vast universe. Some theories even suggest the existence of additional dimensions beyond the 3 spatial dimensions and the temporal dimension that we experience daily. For example, string theory proposes additional dimensions that are too small for us to detect. If these additional dimensions exist, they could contain entire universes with their own sets of physical laws and constants, which could offer information about the structure and limits of our universe. There is also the theory of the cyclic universe, which suggests that the universe goes through endless cycles of expansion and contraction. According to this theory, the universe expands to a certain point, and then gravity pulls everything back into a dense state, leading to a big collapse that triggers another Big Bang. This continuous cycle of creation and destruction suggests that the limit of the universe could simply be a point of transition in an eternal sequence. The universe is expanding, and this expansion affects our ability to observe distant regions. The expansion is driven by dark energy, a mysterious force that accelerates the rate of expansion. As the universe expands, distant galaxies move away from us, and the light from these galaxies shifts to the red at longer wavelengths. The expansion of the universe creates a cosmic horizon, a limit beyond which we cannot see. This horizon is determined by the distance that light has traveled since the Big Bang. As the universe continues to expand, the cosmic horizon will change, potentially revealing new regions of space that were previously beyond our reach. This horizon represents the farthest distance that light has traveled to us from the beginning of the universe. Everything beyond this horizon remains out of our reach, locked by the finite speed of light and the age of the universe. To fully understand what could exist outside the universe, we must consider the nature of space and time according to general relativity. Space and time are intertwined in a four-dimensional continuum known as space-time. The curvature of space-time is determined by the distribution of mass and energy in the universe. If the universe is finite and unbounded, the curvature of space-time could create a closed and autonomous cosmos without external space or time. In this model, asking what exists outside the universe is like asking what is north of the North Pole. It is a question that may not have a meaningful answer within the context of our physical laws. The universe is a vast and mysterious place full of galaxies, stars, planets, and other countless celestial objects. However, one of the most disconcerting discoveries of modern cosmology is that most of the universe, about 95%, is missing matter, which constitutes approximately 5% of the universe, and includes the atoms and particles that form the stars and galaxies. Dark matter, which represents about 27% of the universe, remains invisible and is only detectable through its gravitational effects on visible matter. Dark matter acts as a cosmic framework that guides the structure and formation of galaxies. The concept of dark matter was first proposed in the early 20th century, when astronomers observed an inconsistency between the observed mass of galaxies and the mass deduced from their gravitational effects. In the 1930s, Fritz Zwicky observed that the galaxies in the Coma cluster were moving much faster than expected based solely on visible mass. He hypothesized the presence of dark matter that provided an additional gravitational force. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. Although it does not interact with electromagnetic forces, dark matter exerts a gravitational influence on visible matter, radiation, and the structure of the universe. The most dominant, but difficult to understand, component is dark energy, which constitutes approximately 68% of the universe. This mysterious force drives the accelerated expansion of the universe, acting against the gravitational attraction of matter. Together, these components form the fabric of the cosmos, from the smallest particles to the largest galactic structures. We don't know exactly what dark matter and dark energy are, but we are quite sure they are real. So what is known? Dark matter is essential for the formation of galaxies. When scientists analyze the structure of the universe, they realize that there is not enough regular matter. The gravitational force of the visible matter is not strong enough to form galaxies or complex systems without dark matter. The stars would probably scatter randomly instead of forming the magnificent galaxies that we observe today. This suggests that dark matter acts like glue. This mysterious component that neither emits nor reflects light is known as dark matter. Although it is invisible, dark matter can be observed indirectly. The zones with high concentrations of dark matter deflect the light that passes nearby, a phenomenon known as gravitational lens. This deflection effect acts as a clue that reveals the presence of dark matter through its gravitational interactions. First, we know that dark matter is not simply ordinary matter without stars. Ordinary matter emits detectable particles that make it visible to our instruments. If dark matter were simply ordinary matter, we would have observed it already. Neither is it antimatter. Antimatter emits unique gamma rays when it reacts with normal matter. If dark matter were antimatter, these gamma rays would provide a clear signal that we have not detected. Dark matter is also not made of black holes. Black holes are compact objects that have a strong impact on their environment, while dark matter appears to be scattered throughout the cosmos. The gravitational effects of black holes also differ from what we observe with dark matter. Scientists are exploring diverse ideas and carrying out experiments to discover the true nature of dark matter. Even the precise 15-month study of the cosmos carried out by the Planck spacecraft of the European Space Agency only detected less than 5% of the total observable universe. For years, scientists have tried to solve the mystery of dark matter and have only inferred its existence from the gravitational effect that it seems to have on visible matter. The renowned British physicist Brian Cox explains that dark matter could be some type of particle that we currently do not know, but how do we find dark matter? Scientists are searching for this mysterious dark matter using the world's largest physics experiment at CERN in Switzerland, the Large Hadron Collider. Instead of trying to find it, they're trying to create it from scratch. They do it by colliding known particles at very high speeds to create enormous energy. In these impacts, this energy could produce dark matter particles. When protons collide, they usually create new particles, but these are usually low-mass particles. However, on very rare occasions, these collisions produce much heavier particles, and those are the ones that scientists are looking for. So the search for dark matter continues in the underground laboratories of CERN and observing the night sky. Scientists believe that they are getting closer to discovering its composition. The most popular candidates for dark matter are called WIMPs, or weakly interacting massive particles. It is believed that these particles interact very weakly with normal matter, which makes them incredibly difficult to detect. Underground detectors aim to observe these rare interactions, which provide clues about the nature of dark matter. One of the most fascinating tests comes from gravitational lensing. This phenomenon occurs when light from distant objects, such as galaxies or quasars, occurs around a massive object, such as a cluster of galaxies, due to gravity. The amount of curvature observed can reveal the presence of dark matter, since it contributes to the overall gravitational field. Astronomers also play a key role in the search for dark matter by observing the night sky. They study the behavior of galaxies and clusters of galaxies. The way these enormous structures move and interact provides indirect evidence of the existence of dark matter. For example, the rotation curves of galaxies show the speed at which stars orbit around the center. The gravitational effects that we observe suggest that there is much more mass present, and that is attributed to dark matter. Although we have not yet directly detected dark matter, each experiment brings us closer to understanding this mysterious component of the universe. Dark energy is even more mysterious than dark matter. It is a form of energy that we cannot exactly detect or measure, but we can see its effect. Unlike dark matter, which groups together due to gravity, dark energy is distributed uniformly throughout space. In 1929, the astronomer Edwin Hubble made a revolutionary discovery. He studied how the wavelengths of light from distant galaxies shift towards the red end of the spectrum as they travel through space. This phenomenon, known as redshift, revealed a surprising truth. Hubble discovered that the fainter and more distant galaxies showed a greater redshift, while the closer ones showed less. He concluded that this redshift occurred because the universe is expanding, and as the wavelengths of light stretch, they shift towards the red end of the spectrum, indicating that space itself is growing. Recent findings have taken Hubble's discovery even further. The expansion of the universe not only continues, but is accelerating. Previously, scientists believed that gravity would slow down or even reverse this expansion. Now scientists have discovered that this rapid rate of expansion is due to dark energy, which is separating the universe at an ever-increasing rate. Space itself does not change its properties as it expands, but new space is constantly being created everywhere. Galaxies remain clusters strongly bound by gravity, so we do not experience this expansion in our daily lives, but we see it everywhere in the universe. Wherever there is empty space, more is being formed every second. So what is dark energy? It seems to be some kind of energy in empty space, stronger than anything we know and constantly increasing. Empty space contains more energy than everything else combined in the universe. This mysterious force is pushing galaxies, accelerating the universe's expansion. Dark energy remains a greatest mystery of cosmology. Although we cannot detect or measure it directly, its influence is undeniable on the universe. As we continue exploring and studying the cosmos, we hope to unravel the secrets of this enigmatic force, bringing us closer to understanding the true nature of our ever-expanding universe. The discovery that this expansion is accelerating suggests that a mysterious force called dark energy is acting. Understanding dark energy is one of the greatest challenges of cosmology. Music, today, considering the immensity of the universe, it is intriguing to reflect on our importance within it. Are we unique in the cosmic scheme, or just one of many life forms potentially scattered throughout the cosmos? This leads us to the question, was the universe specifically designed with us in mind? This idea is captured by the anthropic principle, which suggests that the fundamental laws and constants of the universe appear to be precisely calibrated to sustain life, especially intelligent life like that of human beings. For example, the exact values of gravitational force, the intensity of electromagnetic interactions, and the characteristics of atoms are essential for life. Any slight variation in these constants could make life impossible as we know it. So, does this precision in the design of the universe suggest that it was created specifically for us? Some argue that the exact conditions that allow life are too precise to be a mere coincidence, suggesting an intentional creation. Conversely, others argue that this fine-tuning is simply the result of natural processes and chance. They point out that in an immensely vast universe, it is entirely plausible that at least one planet like Earth naturally develops the perfect conditions for life. The multiverse theory adds another layer to this debate, as it proposes that our universe is just one among potentially countless others, each governed by its own set of physical laws and constants. In this vast multiverse, only a select few universes could harbor conditions conducive to life. If this theory is true, our universe is not particularly special. It is simply one of the few where conditions align perfectly for life, making the concept of fine-tuning less extraordinary. The exploration of extraterrestrial life also influences this debate. Discovering life beyond Earth, whether microbial life on Mars, in the hidden oceans of moons like Europa and Enceladus, or on distant exoplanets, would imply that life is not an exclusive phenomenon of Earth, but a widespread phenomenon wherever conditions are favorable. Such discoveries could drastically change our understanding of the rarity of life in the universe beyond the scientific realm. Philosophical opinions also shape our understanding of the universe. Some find comfort in believing that the universe has a deliberate purpose, while others appreciate the beauty of its randomness and its infinite possibilities. Regardless of the intention of the universe, our innate curiosity and our drive to explore are essential human traits, which lead us to delve into these profound questions, not only drive scientific advancement, but also deepen our understanding of the cosmos. Science presents us with a vast and seemingly indifferent universe, which could make us feel insignificant, but some argue that we could still occupy a central role in the cosmos due to the laws of physics, which are finely tuned and make life possible. For example, the electromagnetic force is vital for stars to produce carbon, a fundamental component of life. Even the energy in the vacuum of space seems calibrated for the emergence of intelligent life. This apparent fine-tuning has given rise to various interpretations of the anthropic principle. One perspective postulates that the universe was deliberately designed with us in mind, possibly by an intelligent entity. Another concept, the principle of life, suggests that life is an inherent characteristic of the universe. However, these views are not widely supported in the scientific community. An alternative philosophical interpretation of the anthropic principle is that the universe exists because we are here to observe it. A more pragmatic view holds that the universe seems tailor-made for our existence, simply because we live in a region that allows life. This could be explained by the existence of multiple universes, each governed by different physical laws, ours being one of the few capable of harboring life. We live in a world with 3 dimensions, up and down, left and right, and forward and back. These are the directions in which we can move. Time is another dimension that we experience as we move from the past to the future. Together, they make up what we call space-time. In physics, dimensions are like different directions in which you can move. You can think of them as lines on a graph. We usually only experience 3 dimensions, but what if there are more? The dimensions that we cannot see. Theories such as string theory and M theory of theoretical physics suggest that there could be additional dimensions. According to string theory, the smallest parts of our universe are not points, but tiny vibrating loops of energy called strings. The mathematics behind string theory suggests that 10 or 11 dimensions must exist for everything to work. String theory attempts to explain all the forces of nature, gravity, electromagnetism, and nuclear forces, saying that everything is composed of these strings. The different ways in which the strings vibrate form different particles. Why don't we see these additional dimensions? They could be incredibly small and very folded, making them impossible to detect with our current tools. For example, imagine an ant on a tightrope. For the ant, the rope seems like a line because it cannot see its width. Similarly, these additional dimensions are there, but they are too small or hidden for us to notice. If these superior dimensions exist, they could help us to understand some of the most important questions of physics, such as why gravity is much weaker in comparison with other forces. Perhaps gravity extends into these additional dimensions, which would explain why it seems weaker in our three-dimensional world. The superior dimensions could help us to better understand the basic nature of forces and particles. They could unite all the different natural forces in a great framework that could lead to new technologies and a deeper knowledge of the universe. Scientists are trying to find evidence of these superior dimensions. One way to do it is by looking for small changes in gravity's behavior at very small scales. If the superior dimensions are real, they could cause slight, unusual effects in gravity's functioning that we could detect in laboratory experiments. Another method consists of using collisions of high-energy particles, such as those of the Grand Collisionator to Hadrons, Large Hadron Collider. These experiments collide particles at high speeds, and if some particle disappears into superior dimensions, it could indicate that these dimensions exist. There are also other interesting ideas about superior dimensions. For example, some theories suggest that our universe could be a three-dimensional brain floating in space with more dimensions. In this idea of a cerebral world, our universe could be only one of many parallel universes, each of which would exist as a separate brain in a space with more dimensions. This raises exciting possibilities about how these universes could affect each other, for example, through gravity or the exchange of particles. Another idea related to superior dimensions is the theory of the multiverse. This theory suggests that our universe is only a bubble in a vast sea of other universes, each in a superior dimensional space. These different universes could have their own sets of physical rules and could even interact with each other. For example, when these universes collide, they could create an enormous explosion similar to the Big Bang that started our universe. Although the concept of superior dimensions is fascinating, it is still only a theory. One of the biggest obstacles is that these dimensions are not something we can see or measure directly at present. To detect them, we would need extremely high energy levels or very precise measurements that are beyond our current capabilities. Mathematics is essential to help us understand the concept of superior dimensions. Many theories that suggest the existence of these additional dimensions depend greatly on complex mathematical ideas of geometry, topology, and algebra. These branches of mathematics help us imagine and make sense of spaces that go beyond our usual three-dimensional understanding. Mathematicians and physicists collaborate to create models that pose hypotheses about how these superior dimensions could affect what we observe in the universe. These models are put to the test through various experiments and observations. Quantum mechanics, which studies how particles behave at incredibly small scales, could also be affected by superior dimensions. The strange and often disconcerting behaviors that we see in quantum mechanics could be due to interactions that take place in spaces with more than 3 dimensions. So, do superior dimensions really exist in the universe? Although we still do not have solid evidence, the possibility that superior dimensions exist is an exciting and active field of research in theoretical physics. If these dimensions exist, they could drastically change our understanding of the universe and reveal new secrets about reality's nature. Studying the entire universe is one of science's most ambitious and exciting projects. The universe is immense, extending billions of light years and full of galaxies, stars, planets, and other innumerable celestial objects. To understand the structure, the origins, and the final destiny of the universe, scientists use a variety of tools and methods. Let's explore how we study the universe, from the telescopes that capture its light to the theories that explain its mysteries. Telescopes are the main tools that astronomers use to study the universe. They allow us to observe distant objects by collecting and amplifying their light. There are several types of telescopes, each designed to capture different wavelengths of light and other forms of electromagnetic radiation. Think of the universe as a pie chart with different portions that represent different components. First, we have normal matter, which constitutes only 5% of the universe. This includes the atoms that form the stars, the planets, and everything we see around us. Next, there is dark matter, an unknown type of particle that represents around 25% of the universe. Scientists calculate the amount of dark matter by observing small temperature variations in the cosmic microwave background. These calculations coincide with what we observe in the movements of the stars and galaxies. The CMB comes from an era in which the universe had cooled enough to release the photons from the hot plasma that trapped them for hundreds of thousands of years after the Big Bang, confirming that dark matter was present in the primitive universe. Atoms, or normal matter, only constitute 1/16 of the universe's total mass. Then there is dark energy, a mysterious force responsible for the rapid expansion of the universe. It constitutes 70% of the total matter and energy of the universe. We also have the optical layer, which tells us how much light the universe absorbs and scatters, especially photons. This layer helps us understand the complex processes behind the birth and explosive end of the first stars and the formation of early galaxies. When these first stars and galaxies formed, they emitted intense radiation that broke hydrogen atoms into protons and electrons. This event, known as reionization, caused between 5 and 8% of the CMB photons released during the era of decoupling to be scattered once more. Imagine it as a light fog that appears in a previously clear universe, slightly reducing visibility. To measure this depth of the universe, scientists study the polarization of the CMB, which gives us clues about the early universe and helps us reconstruct the history of how the first stars and galaxies arose. When exploring the mysteries of the universe, we encounter the concept of polarization, which, along with intensity and wavelength, is one of the 3 attributes of a light wave. Some of the fluctuations in the formation of structures in the universe are described by the primordial power spectrum, which describes the variations in the density of the universe through the 3-dimensional space of space in the infancy of the universe. These fluctuations were minor, but as the universe grew, these density variations were magnified. The Scala Spectral Index provides information about the origins of the universe by informing us how these initial fluctuations evolved. Using these 6 parameters, we can calculate not only the properties of the CMB, but also others. For example, we can determine that the age of the universe is 138 billion years, with a margin of error of 40 million years. The most restrictive observation comes from the anisotropy of the CMB, which are subtle temperature variations. The standard cosmological model fits well with all observations from various scientific disciplines, including physics and astronomy. One of the most important tools to study the universe is the telescope. From the first telescopes to modern ones, telescopes allow us to observe distant objects in space, from planets and stars to galaxies and nebulae. There are different types of telescopes designed to observe different wavelengths of light, from visible light to radio waves and even X-rays. Optical telescopes, such as the famous Hubble Space Telescope, capture light in the visible spectrum and provide stunning images of distant galaxies and nebulae. Telescopes like the Arbo Observatory detect radio waves emitted by celestial objects, helping us study phenomena such as pulsars and black holes. X-ray telescopes, such as the Chandra X-ray Observatory, observe high-energy events such as supernovas and the regions around black holes. In addition to telescopes, scientists have launched numerous space missions. Space probes and satellites travel beyond the Earth's atmosphere, providing a clearer view of the cosmos without the interference of our planet's atmosphere. For example, the Voyager probes, launched in the 1970s, have traveled beyond our solar system, sending data about the outer planets and the interstellar medium. The New Horizons mission provided us with the first close-up images of Pluto and continues to explore the Kuiper Belt. In addition, the most advanced telescope, the James Webb Space Telescope, helps study exoplanets and different celestial bodies. One of the key methods for studying the universe as a whole is to examine the cosmic microwave background. The CMB is the afterglow of the Big Bang, a faint radiation that fills the entire universe and provides an image of the cosmos when it was only 380,000 years old. By studying the CMB, scientists can learn about the early conditions of the universe, its composition and age. The Planck satellite provided the most detailed map of the CMB, revealing small fluctuations that tell us about the distribution of matter and energy in the early universe. In addition, scientists conduct large-scale surveys of galaxies. These studies map the positions and properties of millions of galaxies, revealing the cosmic web, a vast network of galaxies and dark matter that stretches across the universe. The Sloan Digital Sky Survey is one of the most comprehensive galaxy surveys, mapping millions of galaxies and helping us understand the large-scale structure of the universe, its expansion, and the distribution of dark matter. While observations provide data, theoretical models and simulations help scientists interpret that data and make predictions about the universe's behavior. There are theoretical models based on the laws of physics and contrasted with observational evidence. Albert Einstein's theory of general relativity describes how gravity works on a cosmic scale and has been crucial to understanding the expansion of the universe, black holes, and the behavior of light in strong gravitational fields. The Big Bang Theory is the main explanation for the origin of the universe. It describes how the universe expanded from an incredibly hot and dense state to its current form. Supercomputers are used to create detailed simulations of the evolution of the universe from the Big Bang to the present. These simulations help scientists study the formation of galaxies, the behavior of dark matter, and the effects of dark energy. Studying the entire universe is a monumental task that requires a combination of advanced technology, innovative theories, and collaboration. Telescopes, both on Earth and in space, provide the data needed to observe the cosmos. Cosmological studies map the large-scale structure of the universe, while theoretical models and simulations help interpret the data and make predictions.